1. Introduction to heat-assisted magnetic recording. 1.1 Overview of magnetic recording. Magnetic recording is a fundamental technology that has revolutionized the way we store and retrieve information. It has been the backbone of various data storage devices, such as hard disk drives (HDDs), for several decades. The concept of magnetic recording is based on the ability of certain materials to retain a magnetic field, which can be used to represent binary data. In traditional magnetic recording, a magnetic field is applied to a recording medium, which aligns the magnetic domains in a specific direction, either parallel or anti-parallel to the field. These aligned domains represent the binary data, with one direction representing a 1 and the other direction representing a 0. The information is then read by detecting the changes in the magnetic field as the read head passes over the medium. While traditional magnetic recording has served us well for many years, it is facing significant challenges as the demand for higher storage capacities continues to grow. The limitations of traditional magnetic recording are becoming more apparent as we approach the physical limits of the materials used and the size of the magnetic domains. To overcome these limitations, researchers and engineers have been exploring alternative approaches to magnetic recording. One such approach is heat-assisted magnetic recording (HAMR), which combines the use of heat and magnetic fields to achieve higher storage densities and improved data reliability. HAMR involves heating a small region of the recording medium using a heat source, such as a laser or a near-field optical device, while applying a magnetic field. The heat temporarily reduces the coercivity of the recording medium, making it easier to write data. Once the data is written, the medium cools down and the magnetic domains become stable, ensuring the long-term retention of the recorded information. The use of heat in HAMR allows for the creation of smaller and more stable magnetic domains, which enables higher storage densities. By reducing the size of the magnetic domains, more data can be packed into the same physical space, leading to increased storage capacities. Additionally, the use of heat helps to overcome the super-paramagnetic limit, which is a phenomenon that occurs when the thermal energy of the medium is sufficient to cause the magnetic domains to randomly flip, resulting in data loss. HAMR also offers improved data reliability compared to traditional magnetic recording. The use of heat allows for more precise control over the writing process, reducing the likelihood of write errors. The smaller and more stable magnetic domains created by HAMR also contribute to improved data integrity and long-term stability. However, HAMR is not without its challenges. One of the main challenges is the development of suitable materials for the recording medium that can withstand the high temperatures involved in the writing process. The recording medium must be able to maintain its magnetic properties even at elevated temperatures to ensure reliable data storage. Another challenge is the design and integration of the heat source into the recording system. The heat source must be able to deliver precise and localized heating to the recording medium without causing any damage. The integration of the heat source with the write head and other components of the recording system requires careful engineering to ensure optimal performance. Furthermore, thermal management is crucial in HAMR systems to prevent overheating and ensure the long-term reliability of the recording medium. Effective thermal management techniques, such as heat sinks and temperature control mechanisms, need to be implemented to dissipate the heat generated during the writing process. Despite these challenges, HAMR holds great promise for the future of magnetic recording. It offers the potential for significantly higher storage densities, which is essential for meeting the ever-increasing demand for data storage. HAMR technology is being actively researched and developed by industry leaders and academic institutions, with the aim of commercializing it in the near future. In the following chapters of this book, we will delve deeper into the various aspects of HAMR technology. We will explore the magnetic materials used in HAMR, the different heat sources employed, the thermal aspects involved, the role of nanoparticles and plasmonics, the design of recording media and write heads, the signal processing techniques, the reliability and durability considerations, and the manufacturing and integration processes. We will also discuss the current applications of HAMR and the future directions and research challenges in this exciting field. So, let us embark on this journey to unleash the power of heat-assisted magnetic recording and explore the fascinating world of HAMR technology. 1.2 Evolution of magnetic recording technology. Magnetic recording technology has come a long way since its inception, evolving significantly over the years to meet the increasing demands for higher storage capacities and faster data transfer rates. This evolution has been driven by advancements in materials, manufacturing processes, and engineering techniques. In this section, we will explore the key milestones in the evolution of magnetic recording technology, leading up to the development of heat-assisted magnetic recording (HAMR). 1.2.1 Early magnetic recording. The history of magnetic recording dates back to the late 19th century when the first magnetic recording device, the telegraphone, was invented by Danish engineer Valdemar Poulsen. This device used a steel wire coated with a magnetic material to record and playback audio signals. However, it was not until the 1950s that magnetic recording technology gained significant traction with the introduction of magnetic tape and magnetic disk storage systems. 1.2.2 Magnetic tape and disk drives. In the 1950s, magnetic tape emerged as a popular medium for data storage. It consisted of a thin plastic film coated with a magnetic material, typically iron oxide. Magnetic tape drives allowed for sequential access to data, making them suitable for applications such as data backup and archival storage. However, they were relatively slow and had limited storage capacities. The 1960s saw the development of magnetic disk drives, which offered random access to data and faster data transfer rates compared to magnetic tape. These early disk drives used large, removable disks coated with a magnetic material. They were primarily used in mainframe computers and were not yet suitable for personal computers due to their size and cost. 1.2.3 Thin film magnetic recording. The 1970s marked a significant milestone in magnetic recording technology with the introduction of thin film magnetic recording. Thin film technology allowed for the deposition of a thin layer of magnetic material directly onto a rigid substrate, such as a metal or glass disc. This enabled higher storage densities and improved performance compared to the earlier magnetic recording technologies. The 1980s witnessed the rapid advancement of thin film magnetic recording, with the introduction of Winchester disk drives. These drives used multiple thin film magnetic disks stacked on a common spindle, providing higher storage capacities and faster data access. Winchester drives became the standard for personal computers and set the stage for the widespread adoption of magnetic disk drives in various applications. 1.2.4 Perpendicular magnetic recording. As the demand for higher storage capacities continued to grow, researchers explored new recording techniques to overcome the limitations of conventional longitudinal magnetic recording. In the late 1990s, perpendicular magnetic recording (PMR) emerged as a promising solution. PMR involved aligning the magnetic grains vertically instead of horizontally, allowing for higher areal densities and improved data stability. PMR technology revolutionized the magnetic recording industry, enabling the development of hard disk drives (HDDs) with terabyte-level storage capacities. It became the dominant recording technology for HDDs and remained so for several years. 1.2.5 Heat-assisted magnetic recording. Despite the advancements in PMR, the quest for even higher storage densities and improved data stability continued. This led to the development of heat-assisted magnetic recording (HAMR) in the early 2000s. HAMR combines the use of a laser or other heat sources with a magnetic recording medium to achieve higher areal densities. In HAMR, a laser is used to heat a small region of the magnetic recording medium, reducing its coercivity temporarily. This allows for more precise writing of magnetic data, enabling higher storage densities. Once the data is written, the medium cools down, and the recorded information becomes stable. HAMR has the potential to push the limits of magnetic recording technology, enabling storage capacities beyond what is currently achievable with PMR. It offers the promise of multi-terabyte HDDs and paves the way for future storage technologies. 1.2.6 Future trends in magnetic recording. The evolution of magnetic recording technology is an ongoing process, driven by the need for higher storage capacities, faster data transfer rates, and improved reliability. While HAMR holds great promise, researchers are already exploring alternative technologies such as microwave-assisted magnetic recording (MAMR) and bit-patterned media recording (BPMR) to further push the boundaries of magnetic storage. MAMR utilizes microwave fields to assist in the writing process, while BPMR involves the use of nanoscale magnetic islands arranged in a regular pattern. These emerging technologies aim to overcome the physical limitations of HAMR and enable even higher storage densities. In conclusion, the evolution of magnetic recording technology has been a remarkable journey, from the early days of magnetic tape to the current era of HAMR. Each milestone has brought us closer to achieving higher storage capacities and faster data access. With ongoing research and development, the future of magnetic recording looks promising, with the potential for even more groundbreaking advancements in the years to come. 1.3 Need for heat-assisted magnetic recording. Magnetic recording technology has been the backbone of data storage for several decades, enabling the storage and retrieval of vast amounts of information. However, as the demand for higher storage capacities and faster data transfer rates continues to grow, traditional magnetic recording methods are reaching their limits. This has led to the development of new technologies, such as heat-assisted magnetic recording (HAMR), to overcome these challenges and meet the ever-increasing demands of the digital age. 1.3.1 Limitations of conventional magnetic recording. Conventional magnetic recording relies on the principle of using a magnetic field to align the magnetic domains of a recording medium, such as a hard disk drive (HDD) platter, to store data. As the demand for higher storage densities has increased, the size of the magnetic domains has decreased, resulting in smaller magnetic grains. However, this reduction in grain size has led to several challenges. One of the main limitations of conventional magnetic recording is the super-paramagnetic effect. When the magnetic grains become too small, thermal fluctuations can cause the magnetic orientation to randomly flip, leading to data corruption. This effect becomes more pronounced as the grain size decreases, making it increasingly difficult to maintain data integrity at higher storage densities. Another limitation is the recording head's ability to generate a strong enough magnetic field to write data onto the smaller magnetic grains. As the grain size decreases, the magnetic field required to write data becomes stronger, pushing the limits of the recording head's capabilities. This limitation is known as the writability limit. Furthermore, the readback signal from the smaller magnetic grains becomes weaker, making it more challenging to accurately detect and retrieve the stored data. This limitation is known as the signal-to-noise ratio (SNR) problem. 1.3.2 Introduction to Heat-Assisted Magnetic Recording. Heat-Assisted Magnetic Recording (HAMR) is a promising technology that aims to overcome the limitations of conventional magnetic recording. HAMR combines the use of a magnetic field with localized heating to enable higher storage densities and improved data integrity. In HAMR, a laser is used to heat a small area of the recording medium, known as the recording spot, to a temperature above its Curie temperature. The Curie temperature is the temperature at which a material loses its magnetic properties. By heating the recording spot, the magnetic grains become more susceptible to the magnetic field generated by the recording head, allowing for more precise and reliable data writing. 1.3.3 Advantages of Heat-Assisted Magnetic Recording. HAMR offers several advantages over conventional magnetic recording, making it a promising technology for future data storage systems. 1. Increased storage density. By using localized heating, HAMR enables the use of smaller magnetic grains, allowing for higher storage densities. The ability to pack more data into a smaller area is crucial for meeting the growing demand for increased storage capacities. 2. Improved data integrity. The use of heat in HAMR helps to overcome the super-paramagnetic effect by stabilizing the magnetic orientation of the grains. By heating the recording spot, the magnetic grains remain stable even at smaller sizes, reducing the risk of data corruption and improving data integrity. 3. Enhanced writability. The localized heating in HAMR reduces the writability limit by making the magnetic grains more responsive to the magnetic field generated by the recording head. This enables more precise and reliable data writing, even on smaller magnetic grains. 4. Higher signal-to-noise ratio. By using smaller magnetic grains, HAMR improves the signal-to-noise ratio, making it easier to detect and retrieve the stored data accurately. This leads to improved readback performance and data reliability. 1.3.4 Challenges of Heat-Assisted Magnetic Recording. While HAMR offers significant advantages, there are also several challenges that need to be addressed for its successful implementation. 1. Thermal stability. Maintaining precise control over the heating process is crucial for the stability and reliability of HAMR. The recording spot needs to be heated to the appropriate temperature without causing excessive heating in the surrounding areas, which could lead to unintended data corruption. 2. Heat dissipation. Efficient heat dissipation is essential to prevent overheating of the recording medium and ensure the longevity of the storage system. Managing the heat generated by the laser and transferring it away from the recording spot is a critical challenge in HAMR. 3. Laser power and reliability. The laser used in HAMR must provide sufficient power to heat the recording spot to the desired temperature consistently. Additionally, the laser's reliability and longevity are crucial factors to ensure the long-term performance and durability of the HAMR system. 4. Compatibility and cost. Integrating HAMR technology into existing data storage systems and infrastructure is a significant challenge. Ensuring backward compatibility with current magnetic recording technologies and minimizing the cost of implementing HAMR are essential considerations for its widespread adoption. In conclusion, the need for heat-assisted magnetic recording (HAMR) arises from the limitations of conventional magnetic recording in meeting the growing demands for higher storage densities and improved data integrity. HAMR offers advantages such as increased storage density, improved data integrity, enhanced writability, and higher signal-to-noise ratio. However, challenges related to thermal stability, heat dissipation, laser power and reliability, and compatibility need to be addressed for the successful implementation of HAMR in future data storage systems. 1.4 Advantages and Challenges of Heat-Assisted Magnetic Recording. Heat-Assisted Magnetic Recording (HAMR) is a promising technology that has the potential to revolutionize the field of magnetic recording. By utilizing a combination of heat and magnetic fields, HAMR offers several advantages over conventional magnetic recording techniques. However, like any emerging technology, HAMR also faces certain challenges that need to be addressed for its successful implementation. In this section, we will explore the advantages and challenges associated with HAMR. 1.4.1 Advantages of Heat-Assisted Magnetic Recording. 1. Increased storage density. One of the primary advantages of HAMR is its ability to achieve higher storage densities compared to conventional magnetic recording technologies. By using heat to temporarily reduce the coercivity of the recording medium, HAMR enables the recording of smaller magnetic domains, allowing for more data to be stored in the same physical space. This increased storage density is crucial in meeting the ever-growing demand for higher capacity storage devices. 2. Enhanced data stability. HAMR offers improved data stability by reducing the susceptibility of recorded data to thermal fluctuations. The use of heat during the recording process allows for a more precise and controlled magnetization of the recording medium, resulting in increased data reliability and longevity. This is particularly important in high-density storage applications where data integrity is paramount. 3. Compatibility with existing infrastructure. Another advantage of HAMR is its compatibility with existing magnetic recording infrastructure. HAMR technology can be integrated into current hard disk drive (HDD) manufacturing processes with minimal modifications, making it a cost-effective solution for increasing storage capacities. This compatibility ensures a smooth transition from conventional magnetic recording to HAMR, minimizing the need for significant changes in manufacturing facilities. 4. Scalability. HAMR offers scalability, allowing for further improvements in storage densities in the future. As the demand for higher capacity storage devices continues to grow, HAMR provides a viable solution to meet these requirements. By leveraging advancements in materials science and heat sources, HAMR can be further optimized to achieve even higher storage densities, ensuring its relevance in the long term. 1.4.2 Challenges of Heat-Assisted Magnetic Recording. 1. Heat management. One of the primary challenges in HAMR is managing the heat generated during the recording process. The precise control of heat is crucial to prevent damage to the recording medium and other components of the storage device. Efficient heat dissipation techniques and thermal management strategies need to be developed to ensure the reliability and longevity of HAMR-based storage devices. 2. Material compatibility. HAMR requires the use of specific magnetic materials that exhibit the desired properties for efficient recording. However, finding materials that can withstand the high temperatures involved in the HAMR process while maintaining their magnetic properties is a significant challenge. Extensive research is being conducted to identify and develop suitable materials that can meet the stringent requirements of HAMR. 3. Manufacturing complexity. Implementing HAMR technology into mass production poses manufacturing challenges. The precise alignment of the heat source, right head, and recording medium is critical for the successful operation of HAMR-based storage devices. Achieving this alignment consistently and accurately during the manufacturing process requires advanced manufacturing techniques and stringent quality control measures. 4. Reliability and durability. Ensuring the reliability and durability of HAMR-based storage devices is crucial for their widespread adoption. The increased complexity of HAMR systems, including the integration of heat sources and the use of new materials, introduces potential reliability issues. Extensive testing and evaluation are necessary to identify and address any reliability concerns, ensuring that HAMR-based storage devices can meet the demanding requirements of various applications. 5. Cost considerations. As with any emerging technology, cost considerations play a significant role in the adoption of HAMR. The development and implementation of HAMR technology require substantial investments in research, development, and manufacturing infrastructure. The cost-effectiveness of HAMR-based storage devices needs to be carefully evaluated to ensure their competitiveness in the market. In conclusion, heat-assisted magnetic recording (HAMR) offers several advantages over conventional magnetic recording technologies, including increased storage density, enhanced data stability, compatibility with existing infrastructure, and scalability. However, HAMR also faces challenges such as heat management, material compatibility, manufacturing complexity, reliability and durability, and cost considerations. Addressing these challenges is crucial for the successful implementation and widespread adoption of HAMR technology in the storage industry. 2. Magnetic materials for heat-assisted magnetic recording. 2.1 Introduction to magnetic materials. Magnetic materials play a crucial role in heat-assisted magnetic recording (HAMR) technology. These materials are responsible for storing and retrieving data in magnetic storage devices such as hard disk drives (HDDs). In this section, we will explore the fundamentals of magnetic materials and their significance in HAMR. 2.1.1 Magnetic properties and performance metrics. To understand the role of magnetic materials in HAMR, it is essential to first comprehend their magnetic properties and performance metrics. Magnetic materials possess the ability to generate and maintain a magnetic field, which allows them to store and retrieve data in magnetic storage devices. One of the key properties of magnetic materials is magnetization, which refers to the alignment of magnetic moments within the material. This alignment determines the strength of the magnetic field generated by the material. The magnetization can be influenced by external factors such as temperature and applied magnetic field. Another important property is coercivity, which measures the resistance of a material to changes in its magnetization. High coercivity is desirable in magnetic storage devices as it ensures the stability of stored data over time. Additionally, remanence, which is the residual magnetization of a material after the external magnetic field is removed, is also a crucial property for data storage. Performance metrics such as magnetic anisotropy, saturation magnetization, and magnetic hysteresis are used to evaluate the suitability of magnetic materials for HAMR. Magnetic anisotropy determines the preferred direction of magnetization within the material, while saturation magnetization represents the maximum magnetization that can be achieved. Magnetic hysteresis measures the energy loss during the magnetization process and affects the efficiency of data storage. 2.1.2 Materials for heat-assisted magnetic recording. In HAMR, the use of specific magnetic materials is essential to achieve high-density data storage. Traditional magnetic materials, such as iron, cobalt, and nickel alloys, have been widely used in magnetic storage devices. However, the demand for higher storage densities and improved thermal stability has led to the exploration of new materials. One of the key requirements for HAMR materials is a high Curie temperature. The Curie temperature is the temperature at which a material undergoes a phase transition and loses its magnetic properties. In HAMR, the recording medium needs to withstand high temperatures generated by the heat source without losing its magnetization. Materials with high Curie temperatures, such as iron platinum Fe-PT alloys and rare earth transition metal ReTM alloys, are being extensively studied for HAMR applications. Another important consideration is the thermal stability of the magnetic materials. As the temperature increases, the thermal fluctuations can cause the magnetization to become unstable, leading to data loss. Materials with high thermal stability, such as granular perpendicular recording media and exchange-coupled composite media, are being investigated to ensure reliable data storage in HAMR. Furthermore, the use of multi-layered structures and thin films is being explored to enhance the performance of magnetic materials in HAMR. These structures allow for better control of the magnetic properties and enable the recording media to achieve higher areal densities. 2.1.3 Advancements in magnetic materials for heat-assisted magnetic recording. The development of advanced magnetic materials is a continuous process driven by the need for higher storage densities and improved performance in HAMR. Researchers are actively exploring various approaches to enhance the magnetic properties of materials used in HAMR. One approach involves the use of magnetic nanoparticles embedded in a non-magnetic matrix. These nanoparticles can exhibit unique magnetic properties, such as high coercivity and thermal stability, which are beneficial for HAMR. Additionally, the integration of plasmonic nanoparticles with magnetic materials has shown promising results in improving the efficiency of heat transfer and enhancing the recording performance. Another area of research focuses on the development of novel magnetic alloys and compounds. For example, the use of rare earth elements in combination with transition metals has shown potential in achieving high thermal stability and improved magnetic properties. Additionally, the exploration of new materials, such as magnetic oxides and nitrides, is opening up new possibilities for HAMR. Advancements in thin film deposition techniques, such as sputtering and atomic layer deposition, have also contributed to the development of high-performance magnetic materials for HAMR. These techniques allow for precise control of film thickness and composition, enabling the fabrication of materials with tailored magnetic properties. In conclusion, magnetic materials are the foundation of HAMR technology, enabling high-density data storage and magnetic storage devices. Understanding the magnetic properties and performance metrics of these materials is crucial for their selection and optimization in HAMR systems. Ongoing research and advancements in magnetic materials continue to drive the progress of HAMR, paving the way for future innovations in data storage technology. 2.2 Magnetic properties and performance metrics. In order to understand the concept of heat-assisted magnetic recording (HAMR), it is essential to have a clear understanding of the magnetic properties and performance metrics of the materials involved. Magnetic materials play a crucial role in HAMR technology as they are responsible for storing and retrieving data. This section will delve into the various magnetic properties and performance metrics that are important in the context of HAMR. 2.2.1 Magnetic properties. Magnetic properties refer to the characteristics of materials that determine their response to an external magnetic field. These properties are crucial in HAMR technology as they directly influence the ability of the material to store and retain data. Some of the key magnetic properties relevant to HAMR are 2.2.1.1 Saturation magnetization. Saturation magnetization is a measure of the maximum magnetic moment per unit volume that a material can achieve when all its magnetic domains are aligned. It represents the upper limit of the magnetic storage capacity of a material. In HAMR, materials with high saturation magnetization are preferred as they can store a larger amount of data. 2.2.1.2 Coercivity. Coercivity is the measure of the resistance of a material to changes in its magnetization. It represents the amount of magnetic field required to demagnetize the material. In HAMR, materials with high coercivity are desirable as they can retain data even in the presence of external magnetic fields. 2.2.1.3 Anisotropy. Anisotropy refers to the directional dependence of a material's magnetic properties. In HAMR, materials with high magnetic anisotropy are preferred as they provide stability to the stored data by maintaining a preferred magnetization direction. This ensures that the data remains intact even in the presence of thermal fluctuations. 2.2.1.4 Curie temperature. Curie temperature is the temperature at which a material undergoes a phase transition from a ferromagnetic to a paramagnetic state. In HAMR, it is important to choose materials with high Curie temperature to ensure that the stored data remains stable at elevated temperatures during the writing process. 2.2.2 Performance metrics. In addition to the magnetic properties, there are several performance metrics that are crucial in evaluating the effectiveness of magnetic materials for HAMR technology. These metrics help in assessing the overall performance and reliability of the recording media. Some of the key performance metrics in HAMR are 2.2.2.1 Bit error rate (BER). Bit error rate is a measure of the number of erroneous bits received compared to the total number of bits transmitted. In HAMR, a low BER is desired to ensure accurate and reliable data storage and retrieval. The magnetic properties of the recording media directly influence the BER, as materials with better magnetic properties exhibit lower error rates. 2.2.2.2 Signal-to-noise ratio (SNR). Signal-to-noise ratio is a measure of the strength of the desired signal compared to the background noise. In HAMR, a high SNR is crucial for accurate data detection. The magnetic properties of the recording media, such as coercivity and anisotropy, directly impact the SNR, as they determine the ability of the material to retain the stored data and minimize noise interference. 2.2.2.3 Writability. Writability refers to the ease with which data can be written onto the recording media. In HAMR, materials with high writability are preferred as they allow for efficient and reliable data recording. The magnetic properties of the recording media, such as saturation magnetization and coercivity, influence the writability by determining the amount of energy required to switch the magnetization direction. 2.2.2.4 Thermal stability. Thermal stability is a measure of the ability of the recording media to retain the stored data at elevated temperatures. In HAMR, materials with high thermal stability are crucial to ensure data integrity during the writing process. The magnetic properties of the recording media, such as anisotropy and Curie temperature, directly impact the thermal stability by providing resistance to thermal fluctuations. 2.2.3 Material selection considerations. The selection of suitable magnetic materials for HAMR involves a careful consideration of the magnetic properties and performance metrics discussed above. The chosen materials should exhibit high saturation magnetization, coercivity, anisotropy, and thermal stability to ensure efficient and reliable data storage. Additionally, the materials should have a high writability and low bit error rate to facilitate accurate data recording and retrieval. Advancements in material science and nanotechnology have led to the development of novel magnetic materials specifically tailored for HAMR applications. These materials exhibit enhanced magnetic properties and performance metrics, making them ideal candidates for HAMR technology. Ongoing research and development efforts continue to explore new materials and optimize their properties to further improve the performance and reliability of HAMR systems. In the next section, we will explore the specific materials that have been developed and utilized for heat-assisted magnetic recording (HAMR) technology. 2.3 Materials for heat-assisted magnetic recording. Heat-assisted magnetic recording (HAMR) is a promising technology that aims to overcome the limitations of conventional magnetic recording by utilizing heat to enhance the writing process. In HAMR, a laser or other heat source is used to locally heat the recording medium, reducing its coercivity and allowing for more precise and efficient writing of data. The success of HAMR relies heavily on the development of suitable materials that can withstand the high temperatures involved and exhibit the desired magnetic properties. 2.3.1 Magnetic recording media. The recording media used in HAMR must possess specific characteristics to ensure reliable and efficient data storage. One of the key requirements is a high magnetic anisotropy, which determines the stability of the recorded data. Materials with high anisotropy are less susceptible to thermal fluctuations, ensuring that the recorded information remains intact over time. Additionally, the media should have a high saturation magnetization to enable efficient writing and reading of data. Traditionally, magnetic materials such as iron, cobalt, and nickel alloys have been used in magnetic recording media. However, these materials have limitations when it comes to HAMR due to their low thermal stability and high Curie temperature. To address these challenges, researchers have been exploring new materials with improved properties. One promising class of materials for HAMR is the rare earth transition metal (ReTM) alloys. These alloys combine the high magnetic anisotropy of rare earth elements with the high saturation magnetization of transition metals. By carefully tuning the composition and microstructure of these alloys, researchers have been able to achieve improved thermal stability and writability. For example, materials such as Fe-PT and L10 ordered COPT have shown great potential for HAMR applications. Another approach to enhancing the thermal stability of recording media is the use of exchange-coupled composite (ECC) structures. ECC media consist of two magnetic layers with different coercivities, separated by a non-magnetic spacer layer. The exchange coupling between the layers allows for the stabilization of the high coercivity layer while maintaining a high saturation magnetization. This design enables better writability and thermal stability compared to single-layer media. In addition to the composition and microstructure, the grain size and grain boundary properties of the recording media also play a crucial role in HAMR performance. Smaller grain sizes are desirable as they allow for higher areal density and improved writability. However, reducing the grain size can lead to increased thermal instability. Therefore, it is essential to find a balance between grain size and thermal stability to optimize the performance of HAMR media. 2.3.2 Plasmonic nanoparticles. Plasmonic nanoparticles have gained significant attention in recent years for their potential applications in HAMR. These nanoparticles, typically made of noble metals such as gold or silver, exhibit unique optical properties due to the excitation of localized surface plasmon resonances. When illuminated with light, plasmonic nanoparticles can generate intense and localized heat, making them suitable for HAMR heat sources. In HAMR, plasmonic nanoparticles can be integrated into the recording media to enhance the heating efficiency and control the heat distribution. By carefully designing the size, shape, and composition of the nanoparticles, researchers can tailor their optical properties to match the laser wavelength used in HAMR systems. This allows for efficient absorption of the laser energy and precise heating of the recording medium. Furthermore, plasmonic nanoparticles can also be used to manipulate the magnetic properties of the recording media. Through the phenomenon of plasmon-induced magnetization switching, the localized heating generated by the nanoparticles can induce changes in the magnetic state of the adjacent recording medium. This opens up new possibilities for controlling the writing process and achieving higher data storage densities. However, the integration of plasmonic nanoparticles into HAMR media poses several challenges. One of the key challenges is the stability of the nanoparticles under high temperature conditions. The thermal stability of the nanoparticles is crucial to ensure their long-term functionality and prevent degradation of the recording media. Researchers are actively exploring different strategies to enhance the stability of plasmonic nanoparticles, such as protective coatings and alloying with other materials. 2.3.3 Other materials considerations. Apart from the recording media and plasmonic nanoparticles, other materials used in HAMR systems also play a vital role in the overall performance and reliability. The heat source, such as a laser or near-field optical source, requires materials that can efficiently convert the input energy into heat. Materials with high absorption coefficients and low thermal conductivity are desirable for effective heat generation and localized heating. Additionally, the materials used in the write heads, which are responsible for generating the magnetic field during the writing process, need to exhibit high magnetic permeability and low coercivity. These properties ensure efficient writing and minimize the energy required for data storage. Various magnetic materials, such as permalloy and KOF alloys, have been extensively studied for write head applications in HAMR. In conclusion, the success of HAMR technology relies on the development of suitable materials that can withstand high temperatures, exhibit desired magnetic properties, and enable efficient heat generation and writing processes. The use of advanced magnetic recording media, plasmonic nanoparticles, and other materials considerations are crucial in realizing the full potential of HAMR for future data storage applications. Ongoing research and advancements in materials science continue to drive the progress of HAMR technology, paving the way for higher data storage densities and improved performance. 2.4 Advancements in magnetic materials for heat-assisted magnetic recording. Heat-assisted magnetic recording, HAMR, is a promising technology that has the potential to significantly increase the storage capacity and data density of magnetic recording systems. One of the key components of HAMR is the magnetic material used in the recording media. Over the years, there have been significant advancements in magnetic materials to meet the requirements of HAMR technology. 2.4.1 High anisotropy materials. One of the main challenges in HAMR is achieving high thermal stability while maintaining a high magnetic coercivity. High anisotropy materials have emerged as a solution to this challenge. These materials have a high magnetic anisotropy, which means that their magnetization is strongly aligned in a specific direction. This property allows for a high coercivity, making the recorded data more stable and less susceptible to thermal fluctuations. Advancements in thin film deposition techniques, such as sputtering and atomic layer deposition, have enabled the fabrication of high anisotropy materials with precise control over their magnetic properties. Materials such as Fe-PT, L10 Fe-PT, and COPT have shown great potential for HAMR applications due to their high anisotropy and excellent thermal stability. 2.4.2 Exchange-coupled composite media. Exchange-coupled composite (ECC) media have gained significant attention in recent years for HAMR applications. ECC media consist of two magnetic layers, a hard magnetic layer and a soft magnetic layer. The exchange coupling between these layers allows for a high coercivity and thermal stability while maintaining a low switching field. Advancements in fabrication techniques have enabled the precise control of the exchange coupling between the hard and soft magnetic layers, leading to improved performance of ECC media. The use of materials such as Fe-PT and COPT as the hard magnetic layer and FeCO or Feni as the soft magnetic layer has shown promising results in terms of thermal stability and writability. 2.4.3 Granular media. Granular media, which consist of magnetic grains dispersed in a non-magnetic matrix, have been extensively studied for HAMR applications. The size and composition of the magnetic grains play a crucial role in determining the magnetic properties of the media. Advancements in nanofabrication techniques have allowed for the precise control of the grain size and composition, leading to improved performance of granular media. Smaller grain sizes have been achieved, which results in higher areal density and improved writability. Additionally, the use of materials with high magnetic anisotropy, such as Fe-PT and COPT, as the magnetic grains has further enhanced the thermal stability of granular media. 2.4.4 Perpendicular magnetic recording (PMR) media. Perpendicular magnetic recording (PMR) media have been widely used in conventional magnetic recording systems. In PMR, the magnetization of the recording layer is oriented perpendicular to the plane of the media, which allows for higher areal density and improved writability. Advancements in PMR media have also contributed to the development of HAMR technology. The use of materials with high magnetic anisotropy, such as co-CrPtCO2 and co-CrPtTaOx, as the recording layer in PMR media has shown promising results in terms of thermal stability and writability. Additionally, the introduction of exchange-coupled composite structures in PMR media has further improved their performance for HAMR applications. 2.4.5 Hybrid media. Hybrid media, which combine different magnetic materials, have emerged as a potential solution to overcome the limitations of individual materials in HAMR. By combining materials with complementary properties, hybrid media aim to achieve a balance between thermal stability, writability, and areal density. Advancements in material synthesis and characterization techniques have enabled the development of hybrid media with improved performance. For example, the combination of high anisotropy materials with granular media or ECC structures has shown promising results in terms of thermal stability and writability. 2.4.6 Novel materials. In addition to the advancements in existing magnetic materials, researchers are also exploring the use of novel materials for HAMR applications. These materials include rare earth transition metal alloys, Heusler alloys, and magnetic oxides. The unique properties of these novel materials, such as high magnetic anisotropy, low Gilbert damping, and tunable magnetic properties, make them attractive candidates for HAMR technology. However, further research is needed to understand their compatibility with HAMR systems and to optimize their performance for practical applications. In conclusion, advancements in magnetic materials have played a crucial role in the development of heat-assisted magnetic recording technology. High anisotropy materials, exchange-coupled composite media, granular media, PMR media, hybrid media, and novel materials have all contributed to improving the thermal stability, writability, and areal density of HAMR systems. Continued research and development in magnetic materials are expected to further enhance the performance and reliability of HAMR technology, paving the way for its widespread adoption in the future. 3. Heat sources for heat-assisted magnetic recording. 3.1 Introduction to heat sources. Heat-assisted magnetic recording (HAMR) is a promising technology that aims to overcome the limitations of conventional magnetic recording by utilizing heat to enhance the writing process. In HAMR, a localized heat source is used to temporarily reduce the coercivity of the recording medium, allowing for more precise and efficient writing of data. The heat source plays a crucial role in HAMR, as it determines the effectiveness and reliability of the recording process. In this section, we will explore the different heat sources used in HAMR and discuss their advantages, limitations, and suitability for practical implementation. We will examine three main heat sources: laser heating, near-field optical heating, and microwave heating. 3.1.1 Laser heating for heat-assisted magnetic recording. Laser heating is the most widely used heat source in HAMR. It involves focusing a laser beam onto the recording medium to generate localized heat. The laser beam is typically directed through an optical waveguide and focused onto a small spot on the recording medium. The heat generated by the laser causes a temporary reduction in the coercivity of the medium, allowing for more efficient writing of data. One of the key advantages of laser heating is its high spatial and temporal control. The laser beam can be precisely focused onto a small area, enabling highly localized heating. This allows for the writing of smaller magnetic domains, leading to increased areal density and higher storage capacity. Laser heating also offers fast heating and cooling rates, which are essential for achieving high data transfer rates. However, laser heating also presents some challenges. One of the main challenges is the need for a reliable and stable laser source. The laser must provide a consistent and controlled amount of heat to ensure accurate writing of data. Additionally, the laser beam must be precisely aligned with the recording medium to achieve optimal heating. Any misalignment can result in reduced writing performance and data errors. 3.1.2 Near-field optical heating for heat-assisted magnetic recording. Near-field optical heating is an alternative heat source that has gained attention in recent years. It involves using a near-field transducer (NFT) to generate localized heat in close proximity to the recording medium. The NFT consists of a metallic nanostructure that can efficiently convert optical energy into heat. The heat generated by the NFT is then transferred to the recording medium, enabling precise writing of data. One of the advantages of near-field optical heating is its ability to achieve even higher spatial resolution compared to laser heating. The NFT can be designed to have a smaller heat spot size, allowing for the writing of even smaller magnetic domains. This can further increase the areal density and storage capacity of the recording medium. Near-field optical heating also offers the potential for lower power consumption, as the heat is generated in close proximity to the recording medium. However, near-field optical heating also has its limitations. One of the main challenges is the fabrication and integration of the NFT into the recording system. The NFT must be carefully designed and manufactured to ensure efficient heat generation and transfer. Additionally, the NFT must be positioned in close proximity to the recording medium, which requires precise alignment and control. Any misalignment or variation in the NFT performance can significantly impact the writing process. 3.1.3 Microwave heating for heat-assisted magnetic recording. Microwave heating is another heat source that has been explored for HAMR. It involves using microwave radiation to generate heat in the recording medium. The microwave radiation is absorbed by the recording medium, causing localized heating and reduction in coercivity. Microwave heating offers the advantage of non-contact heating, as the heat is generated remotely without the need for direct physical contact. One of the main advantages of microwave heating is its potential for high heating efficiency. Microwave radiation can penetrate the recording medium more deeply compared to laser or near-field optical heating, allowing for more uniform and efficient heating. Microwave heating also offers the advantage of scalability, as it can be easily applied to larger recording areas. However, microwave heating also presents challenges. One of the main challenges is the need for precise control of the heating process. The microwave power must be carefully controlled to ensure optimal heating without causing excessive temperature rise or thermal damage to the recording medium. Additionally, the microwave radiation must be carefully focused onto the recording medium to achieve localized heating. Any variation in the microwave power or focusing can result in reduced writing performance and data errors. In conclusion, heat sources play a critical role in heat-assisted magnetic recording (HAMR) technology. Laser heating, near-field optical heating, and microwave heating are the main heat sources used in HAMR. Each heat source offers unique advantages and challenges, and their suitability for practical implementation depends on factors such as spatial resolution, power consumption, fabrication complexity, and control requirements. Further research and development are needed to optimize the performance and reliability of heat sources in HAMR systems. 3.2 Laser heating for heat-assisted magnetic recording. Laser heating is one of the most widely used heat sources in heat-assisted magnetic recording (HAMR) technology. It plays a crucial role in achieving the high temperatures required to reduce the coercivity of the recording media and enable writing of data at high areal densities. In this section, we will explore the principles of laser heating, its advantages and challenges, and the advancements made in this field. Principles of laser heating. Laser heating involves the use of a focused laser beam to heat a small region on the surface of the recording media. The laser beam is typically generated by a laser diode and is directed onto the media through an optical system. The laser power and duration are carefully controlled to ensure precise heating of the media. The laser beam interacts with the media, causing localized heating through the absorption of laser energy. This heating process raises the temperature of the media above its Curie temperature, which reduces the coercivity of the material. The magnetic write head then applies a magnetic field to align the magnetic domains in the heated region, allowing data to be written. Advantages of laser heating. Laser heating offers several advantages in HAMR technology. Firstly, it provides precise and localized heating, allowing for high-resolution writing of data. The focused laser beam enables the creation of smaller and more densely packed magnetic domains, leading to increased areal density and storage capacity. Secondly, laser heating allows for rapid heating and cooling of the media. The laser can be turned on and off quickly, enabling fast writing speeds and reducing the time required for data recording. This is particularly important in high-performance storage devices where fast data transfer rates are essential. Furthermore, laser heating offers flexibility in terms of the wavelength and power of the laser beam. Different materials have different absorption characteristics, and by selecting an appropriate laser wavelength, the heating efficiency can be optimized. Additionally, the power of the laser beam can be adjusted to control the temperature rise, ensuring the media reaches the desired temperature without causing damage. Challenges of laser heating. While laser heating has numerous advantages, it also presents certain challenges that need to be addressed for successful implementation in HAMR technology. One of the main challenges is achieving uniform heating across the media surface. Variations in the media composition, thickness, and surface roughness can lead to uneven heating, resulting in non-uniform magnetic properties and data errors. Efforts are being made to develop advanced optical systems and feedback control mechanisms to overcome this challenge. Another challenge is the thermal management of the media during the writing process. The localized heating caused by the laser beam can generate significant heat, which needs to be dissipated efficiently to prevent overheating and thermal damage. Effective thermal management techniques, such as the use of heat sinks and thermal insulation layers, are being explored to ensure the reliability and durability of the recording media. Advancements in laser heating. Significant advancements have been made in laser heating technology for HAMR. Researchers have been exploring various laser sources, including solid-state lasers, fiber lasers, and semiconductor lasers, to improve the efficiency and reliability of laser heating. These lasers offer different characteristics in terms of power, wavelength, and beam quality, allowing for better control and optimization of the heating process. Moreover, advancements in laser beam shaping techniques have enabled the creation of more precise and uniform heating profiles. By shaping the laser beam intensity and distribution, the heating can be tailored to match the desired magnetic domain size and shape, further enhancing the writing performance and data integrity. Furthermore, research is being conducted to develop novel materials with enhanced optical and thermal properties for improved laser absorption and heat transfer. These materials aim to maximize the efficiency of laser heating while minimizing the energy required, leading to more energy-efficient HAMR systems. In conclusion, laser heating is a key heat source in HAMR technology, enabling high-density data recording. Its precise and localized heating capabilities, along with rapid heating and cooling, offer significant advantages for achieving higher areal densities and faster writing speeds. However, challenges related to uniform heating and thermal management need to be addressed for successful implementation. Ongoing advancements in laser sources, beam shaping techniques, and materials are paving the way for further improvements in laser heating for HAMR systems. 3.3 Near-field optical heating for heat-assisted magnetic recording. Near-field optical heating is a promising technique for heat-assisted magnetic recording, HAMR, that utilizes the interaction between light and matter at nanoscale distances. This technique involves the use of a near-field optical transducer, NFOT, to deliver localized heating to the recording medium, enabling precise control over the temperature of the magnetic grains during the writing process. 3.3.1 Introduction to Near-field optical heating. Near-field optical heating relies on the phenomenon of plasmonics, which involves the interaction between light and metallic nanoparticles. When light is incident on a metallic nanoparticle, it excites the collective oscillation of free electrons, known as surface plasmons. These surface plasmons generate intense electromagnetic fields in the vicinity of the nanoparticle, which can be used to heat the surrounding medium. In the context of HAMR, near-field optical heating involves the integration of plasmonic nanoparticles into the right head of the recording system. These nanoparticles, typically made of noble metals such as gold or silver, are designed to resonate at specific wavelengths of light, allowing for efficient absorption and conversion of optical energy into heat. By controlling the intensity and wavelength of the incident light, the temperature of the recording medium can be precisely modulated. 3.3.2 Advantages of near-field optical heating. Near-field optical heating offers several advantages over other heat sources used in HAMR. One of the key advantages is its ability to provide highly localized heating. The near-field region, which extends only a few nanometers from the surface of the nanoparticles, allows for precise control over the temperature of individual magnetic grains. This localized heating minimizes the risk of thermal interference with neighboring grains, ensuring high data density and reliable recording. Another advantage of near-field optical heating is its fast heating and cooling rates. The intense electromagnetic fields generated by the plasmonic nanoparticles enable rapid energy transfer to the recording medium, resulting in faster write speeds. Additionally, the localized nature of the heating process allows for efficient cooling, reducing the time required for the medium to reach its magnetic coercivity temperature. Furthermore, near-field optical heating offers compatibility with high areal density recording media. The small size of the plasmonic nanoparticles enables their integration into the right head without significantly affecting the overall dimensions of the recording system. This compatibility is crucial for achieving the desired areal density improvements in HAMR. 3.3.3 Challenges and Considerations. Despite its potential advantages, near-field optical heating also presents certain challenges and considerations that need to be addressed for successful implementation in HAMR systems. One of the challenges is the optimization of the plasmonic nanoparticles for efficient light absorption and heat generation. The size, shape, and composition of the nanoparticles play a crucial role in determining their plasmonic properties. Extensive research is being conducted to design and engineer nanoparticles that exhibit strong plasmonic resonances at the desired wavelengths of light used in HAMR. Another consideration is the thermal stability of the plasmonic nanoparticles. The intense electromagnetic fields generated during near-field optical heating can cause localized heating of the nanoparticles themselves, leading to thermal degradation or melting. Therefore, it is essential to select materials and designs that can withstand the high temperatures generated during the writing process. Furthermore, the integration of the plasmonic nanoparticles into the right head requires careful engineering to ensure their proper alignment and positioning. Precise control over the distance between the nanoparticles and the recording medium is crucial for achieving optimal heating efficiency and minimizing thermal interference with neighboring grains. 3.3.4 Research and Development. The field of near-field optical heating for HAMR is still undergoing active research and development. Scientists and engineers are exploring various approaches to optimize the performance and reliability of this technique. One area of research focuses on the development of novel plasmonic materials and structures. By tailoring the properties of the nanoparticles, such as their size, shape, and composition, researchers aim to enhance their plasmonic resonances and improve their heat generation capabilities. Additionally, efforts are being made to explore alternative materials beyond noble metals that can exhibit strong plasmonic effects. Another research direction involves the investigation of alternative light sources for near-field optical heating. While laser diodes are commonly used in HAMR systems, other light sources such as light-emitting diodes, LEDs, and semiconductor lasers are being explored for their potential advantages in terms of cost, power efficiency, and wavelength tunability. Furthermore, researchers are working on developing advanced fabrication techniques for the integration of plasmonic nanoparticles into the right head. These techniques aim to achieve precise control over the size, shape, and positioning of the nanoparticles, ensuring optimal heating performance and long-term reliability. 3.3.5 Conclusion. Near-field optical heating holds great promise for advancing the field of heat-assisted magnetic recording. Its ability to provide highly localized and fast heating, along with compatibility with high areal density recording media, makes it a compelling heat source for HAMR systems. However, further research and development are required to overcome the challenges and optimize the performance of near-field optical heating for practical implementation in commercial HAMR devices. 3.4 Microwave heating for heat-assisted magnetic recording. Microwave heating is a promising technique for heat-assisted magnetic recording, HAMR, due to its ability to generate localized and rapid heating. In this section, we will explore the principles of microwave heating and its application in HAMR systems. 3.4.1 Introduction to microwave heating. Microwave heating is a process that utilizes electromagnetic waves in the microwave frequency range to generate heat. These waves interact with the material being heated, causing the molecules to vibrate and generate heat through friction. The advantage of microwave heating lies in its ability to penetrate materials and generate heat directly within the target area, making it suitable for localized heating applications such as HAMR. 3.4.2 Microwave-Assisted HAMR Systems. In a microwave-assisted HAMR system, a microwave source is integrated into the recording head to provide the necessary heat for writing data onto the magnetic media. The microwave energy is focused onto the recording area, raising the temperature of the magnetic media above its Curie temperature, which reduces its coercivity and allows for easier magnetization. This enables higher areal densities and improved data storage capabilities. 3.4.3 Advantages of microwave heating in HAMR. Microwave heating offers several advantages in HAMR systems compared to other heat sources. Firstly, microwave energy can be precisely controlled and focused, allowing for localized heating of the recording area. This ensures that only the desired region is heated, minimizing the risk of overheating and potential damage to the media. Additionally, microwave heating is fast and efficient, enabling rapid temperature rise and fall, which is crucial for high-speed data writing in HAMR. Another advantage of microwave heating is its compatibility with various recording media materials. Unlike laser heating, which may have limitations in terms of the media's absorption properties, microwave heating can be tailored to match the specific absorption characteristics of different media materials. This flexibility allows for a wider range of media options and potential improvements in recording performance. 3.4.4 Challenges and Considerations. While microwave heating shows great potential for HAMR, there are several challenges and considerations that need to be addressed. One of the main challenges is the design and integration of the microwave source into the recording head. The size and power requirements of the microwave source need to be carefully balanced to ensure efficient heating without compromising the overall performance and reliability of the HAMR system. Another consideration is the potential interference between the microwave energy and the magnetic field used for writing data. The presence of microwave energy in the recording area may affect the magnetic field distribution, leading to variations in the written data. This interference needs to be minimized through careful design and optimization of the HAMR system. Furthermore, the thermal stability and reliability of the media under microwave heating need to be thoroughly investigated. The rapid temperature rise and fall associated with microwave heating may introduce thermal stresses and affect the long-term durability of the media. Understanding the thermal behavior and reliability of the media is crucial for ensuring the longevity and performance of HAMR systems. 3.4.5 Research and Development. Research and development efforts are ongoing to further explore the potential of microwave heating in HAMR systems. One area of focus is the optimization of microwave sources to improve their efficiency and power output. This includes the development of compact and high-power microwave sources that can be integrated into the recording head without compromising the overall performance of the system. Another area of research is the investigation of novel media materials that exhibit enhanced absorption properties for microwave energy. By tailoring the media's composition and structure, researchers aim to improve the efficiency of microwave heating and further enhance the performance of HAMR systems. Additionally, studies are being conducted to better understand the thermal behavior and reliability of media under microwave heating. This includes the characterization of thermal stability, thermal stress analysis, and long-term durability testing. The findings from these studies will contribute to the development of reliable and robust HAMR systems. Conclusion. Microwave heating offers a promising approach for heat-assisted magnetic recording (HAMR) systems. Its ability to provide localized and rapid heating, along with its compatibility with various media materials, makes it an attractive heat source for HAMR. However, challenges such as integration, interference, and thermal stability need to be addressed to fully realize the potential of microwave heating in HAMR systems. Ongoing research and development efforts aim to overcome these challenges and further improve the performance and reliability of HAMR technology. 3.5 Comparison of heat sources for heat-assisted magnetic recording. Heat-assisted magnetic recording (HAMR) is a promising technology that aims to overcome the super-paramagnetic limit and increase the areal density of magnetic storage devices. In HAMR, heat is used to temporarily reduce the coercivity of the recording medium, allowing for more precise and reliable writing of data. The heat source plays a crucial role in the success of HAMR, as it determines the efficiency, reliability, and scalability of the technology. In this section, we will compare the three main heat sources used in HAMR: laser heating, near-field optical heating, and microwave heating. 3.5.1 Laser heating. Laser heating is the most widely used heat source in HAMR. It involves focusing a laser beam onto the recording medium to generate localized heating. The laser beam is typically guided through an optical waveguide and directed onto the recording medium using a near-field transducer (NFT). The NFT converts the optical energy into heat, which raises the temperature of the recording medium above its Curie temperature, allowing for easier magnetization. One of the key advantages of laser heating is its high spatial and temporal control. The laser beam can be precisely focused on a small area, enabling highly localized heating and writing of data. Moreover, the laser can be rapidly turned on and off, allowing for fast data writing and high data transfer rates. Laser heating also offers excellent scalability, as the laser power can be easily adjusted to meet the requirements of different storage densities. However, laser heating also has some limitations. One of the main challenges is the need for a reliable and efficient NFT. The NFT must efficiently convert the optical energy into heat and transfer it to the recording medium without causing any damage. The design and fabrication of the NFT are critical to ensure optimal heat transfer and minimize energy losses. Another challenge is the potential for thermal diffusion, where the heat spreads beyond the intended region, leading to unwanted thermal effects and reduced data reliability. 3.5.2 Near-Field Optical Heating. Near-field optical heating (NFOH) is an alternative heat source for HAMR that utilizes the near-field interaction between a plasmonic structure and the recording medium. Unlike laser heating, which relies on the direct absorption of light by the recording medium, NFOH uses the localized electromagnetic field enhancement near the plasmonic structure to induce heating. This localized heating effect allows for precise control of the temperature distribution and reduces the risk of thermal diffusion. One of the main advantages of NFOH is its potential for higher energy efficiency compared to laser heating. The plasmonic structure can be designed to enhance the absorption of light by the recording medium, reducing the required optical power and improving the overall energy efficiency of the system. NFOH also offers the possibility of multi-bit writing, where multiple bits can be written simultaneously by controlling the temperature distribution with different plasmonic structures. However, NFOH also has some challenges that need to be addressed. One of the main challenges is the design and fabrication of the plasmonic structures. The plasmonic structures must be carefully engineered to achieve the desired near-field enhancement and efficient heat transfer. The choice of materials and the optimization of the plasmonic structure's geometry are critical to ensure optimal performance. Another challenge is the potential for plasmonic heating-induced thermal effects, such as thermal expansion and stress, which can affect the reliability and durability of the recording medium. 3.5.3 Microwave Heating. Microwave heating is another heat source that has been explored for HAMR. It involves the use of microwaves to induce heating in the recording medium. The microwaves can be generated using a microwave antenna or a microwave cavity, and they penetrate the recording medium to raise its temperature above the Curie temperature. Microwave heating offers the advantage of non-contact heating, as the microwaves can penetrate through protective layers and heat the recording medium directly. One of the main advantages of microwave heating is its potential for high heating efficiency. Microwaves can efficiently couple with the recording medium and generate localized heating without the need for direct contact. This can lead to improved energy efficiency and reduced thermal effects on the surrounding components. Microwave heating also offers the possibility of multi-bit writing, similar to NFOH, by controlling the microwave power and frequency. However, microwave heating also has some challenges that need to be addressed. One of the main challenges is the design and optimization of the microwave antenna or cavity. The antenna or cavity must be carefully designed to achieve efficient coupling with the recording medium and minimize energy losses. The choice of materials and the geometry of the antenna or cavity are critical to ensure optimal performance. Another challenge is the potential for electromagnetic interference (EMI) and crosstalk, as the microwaves can interact with other components in the storage device and affect their performance. 3.5.4 Comparison and Future Directions. Each heat source for HAMR has its advantages and challenges. Laser heating offers high spatial and temporal control, making it suitable for high-density storage applications. Near-field optical heating offers the potential for higher energy efficiency and multi-bit writing. Microwave heating offers non-contact heating and high heating efficiency. The choice of heat source depends on the specific requirements of the storage system, such as the desired areal density, data transfer rate, and energy efficiency. In the future, further advancements in heat source technologies are expected. Researchers are exploring new materials and designs for NFTs, plasmonic structures, and microwave antennas or cavities to improve their efficiency and reliability. Additionally, hybrid heat sources that combine the advantages of laser heating, near-field optical heating, and microwave heating are being investigated to overcome the limitations of individual heat sources. These advancements will contribute to the continued development and commercialization of HAMR technology, enabling higher areal densities and improved performance in magnetic storage devices. 4. Thermal aspects in heat-assisted magnetic recording. 4.1 Thermal modeling and simulation. Thermal modeling and simulation play a crucial role in understanding and optimizing the performance of heat-assisted magnetic recording (HAMR) systems. By accurately predicting the temperature distribution and thermal behavior within the recording medium, these techniques enable engineers to design more efficient and reliable HAMR systems. 4.1.1 Introduction to Thermal Modeling and Simulation. Thermal modeling involves the mathematical representation of the physical processes that govern heat transfer within the HAMR system. It aims to capture the complex interactions between the heat source, recording medium, and surrounding components. Simulation, on the other hand, utilizes these mathematical models to predict the temperature distribution and thermal behavior under various operating conditions. The primary goal of thermal modeling and simulation in HAMR is to optimize the heat delivery to the recording medium while ensuring thermal stability and reliability. By accurately predicting the temperature rise and distribution, engineers can design HAMR systems that achieve the desired recording performance without compromising the durability of the recording medium. 4.1.2 Modeling heat transfer mechanisms. In HAMR systems, heat is primarily transferred through three mechanisms: conduction, convection, and radiation. Conduction refers to the transfer of heat through direct contact between materials, while convection involves the transfer of heat through the movement of a fluid medium. Radiation, on the other hand, occurs through the emission and absorption of electromagnetic waves. Thermal modeling and simulation techniques consider these heat transfer mechanisms to accurately predict the temperature distribution within the recording medium. By incorporating the material properties, geometry, and operating conditions of the HAMR system, engineers can simulate the heat transfer process and evaluate its impact on the recording performance. 4.1.3 Finite element analysis (FEA) for thermal modeling. Finite element analysis (FEA) is a widely used technique for thermal modeling and simulation in HAMR systems. FEA divides the HAMR system into small, interconnected elements and solves the governing heat transfer equations for each element. By considering the material properties, boundary conditions, and heat sources, FEA provides a detailed and accurate representation of the temperature distribution within the system. FEA allows engineers to analyze the impact of various design parameters on the thermal behavior of the HAMR system. By modifying the geometry, material properties, or heat source characteristics, engineers can evaluate the effect on the temperature rise, thermal stability, and reliability of the recording medium. This information is crucial for optimizing the design and performance of HAMR systems. 4.1.4 Challenges in thermal modeling and simulation. Thermal modeling and simulation in HAMR systems present several challenges due to the complex nature of heat transfer and the interaction between different components. One of the main challenges is accurately capturing the heat generation and dissipation within the recording medium. The heat source, such as a laser or near-field transducer, must be accurately modeled to predict its impact on the temperature distribution. Another challenge is the accurate representation of the material properties of the recording medium. The thermal conductivity, specific heat, and other material properties can vary with temperature, making it essential to consider these variations in the modeling process. Additionally, the presence of nanoparticles or plasmonic structures in the recording medium can further complicate the thermal modeling process. Furthermore, the transient nature of the heat transfer process in HAMR systems poses a challenge for accurate simulation. The temperature rise and distribution change rapidly during the recording process, requiring sophisticated numerical techniques to capture these dynamics. Time-dependent simulations are necessary to accurately predict the thermal behavior and ensure the reliability of the recording medium. 4.1.5 Benefits and applications of thermal modeling and simulation. Thermal modeling and simulation provide numerous benefits in the development and optimization of HAMR systems. By accurately predicting the temperature distribution, engineers can optimize the heat delivery to the recording medium, ensuring efficient and reliable recording performance. This optimization can lead to higher areal densities, increased storage capacity, and improved data transfer rates in HAMR-based storage devices. Furthermore, thermal modeling and simulation enable engineers to evaluate the impact of different design parameters on the thermal behavior of the HAMR system. By studying the effects of heat source characteristics, material properties, and system geometry, engineers can identify the optimal design configurations that maximize the recording performance while ensuring the durability and reliability of the recording medium. Thermal modeling and simulation also find applications in the development of thermal management techniques for HAMR systems. By understanding the temperature distribution within the system, engineers can design effective cooling mechanisms to dissipate the excess heat generated during the recording process. This ensures the long-term reliability and durability of the recording medium, extending the lifespan of HAMR-based storage devices. In conclusion, thermal modeling and simulation are essential tools in the development and optimization of heat-assisted magnetic recording systems. By accurately predicting the temperature distribution and thermal behavior, engineers can design HAMR systems that achieve high recording performance while ensuring the durability and reliability of the recording medium. These techniques enable the advancement of HAMR technology, leading to higher areal densities, increased storage capacity, and improved data transfer rates in next-generation storage devices. 4.2 Heat transfer mechanisms in heat-assisted magnetic recording. Heat-assisted magnetic recording (HAMR) is a promising technology that enables higher areal density in magnetic recording systems. In HAMR, heat is used to temporarily reduce the coercivity of the recording medium, allowing for more precise and reliable writing of data. The efficient transfer of heat is crucial for the success of HAMR, as it directly affects the performance and reliability of the recording system. In this section, we will explore the various heat transfer mechanisms involved in HAMR and their impact on the recording process. 4.2.1 Conduction heat transfer. Conduction heat transfer is one of the primary mechanisms involved in HAMR. It occurs when heat is transferred through direct contact between two objects with different temperatures. In the context of HAMR, conduction heat transfer takes place between the heat source, such as a laser or near-field transducer (NFT), and the recording medium. The efficiency of conduction heat transfer depends on the thermal conductivity of the materials involved. The thermal conductivity of the recording medium is a critical parameter in HAMR. It determines how effectively heat can be conducted from the heat source to the recording medium. Materials with higher thermal conductivity facilitate better heat transfer, ensuring that the recording medium reaches the desired temperature quickly and uniformly. Researchers have been actively exploring materials with high thermal conductivity, such as diamond-like carbon (DLC) and various metal alloys, to enhance the performance of HAMR systems. 4.2.2 Radiative heat transfer. Radiative heat transfer plays a significant role in HAMR, particularly when laser heating is employed as the heat source. It involves the transfer of heat through electromagnetic radiation. In HAMR, the laser emits a focused beam of light onto the recording medium, which absorbs the radiation and converts it into heat. The efficiency of radiative heat transfer depends on factors such as the intensity and wavelength of the laser, as well as the absorption properties of the recording medium. The absorption properties of the recording medium are crucial for efficient radiative heat transfer. The recording medium should have a high absorption coefficient at the laser wavelength to ensure maximum energy absorption. Additionally, the reflectivity of the recording medium should be minimized to prevent energy loss through reflection. Researchers have been investigating various materials and coatings to optimize the absorption properties of the recording medium, aiming to achieve efficient heat transfer and precise temperature control. 4.2.3 Convective heat transfer. Convective heat transfer occurs when heat is transferred through the movement of a fluid, such as air or a liquid. In the context of HAMR, convective heat transfer can influence the cooling process after the heat has been applied to the recording medium. Efficient cooling is essential to ensure the stability and reliability of the recording system. Convective heat transfer can be enhanced by designing appropriate cooling mechanisms, such as heat sinks or fluid channels, to facilitate the removal of excess heat. The design of the cooling system is crucial for effective convective heat transfer in HAMR. It should be optimized to provide sufficient cooling capacity while minimizing any adverse effects on the recording medium or other components of the system. The flow rate, temperature, and pressure of the cooling fluid should be carefully controlled to ensure efficient heat dissipation. Researchers are continuously exploring innovative cooling solutions to improve the thermal management of HAMR systems. 4.2.4 Phase change heat transfer. Phase change heat transfer involves the transfer of heat during a phase transition, such as from solid to liquid or liquid to gas. In HAMR, phase change heat transfer can occur when the recording medium undergoes a phase transition due to the applied heat. The phase change process can affect the magnetic properties of the recording medium, influencing the writing and stability of the recorded data. Understanding and controlling phase change heat transfer is crucial for achieving reliable and high-performance HAMR systems. The phase change behavior of the recording medium is a critical consideration in HAMR. The recording medium should exhibit a well-defined phase change temperature, allowing for precise control of the writing process. Additionally, the phase change should be reversible, ensuring the stability and reliability of the recorded data. Researchers are actively investigating various materials and compositions to optimize the phase change properties of the recording medium, aiming to achieve reliable and efficient HAMR systems. 4.2.5 Combined heat transfer mechanisms. In HAMR, multiple heat transfer mechanisms often work together to achieve efficient and controlled heating and cooling. The combination of conduction, radiation, convection, and phase change heat transfer mechanisms can significantly impact the overall performance and reliability of the recording system. Understanding the interplay between these mechanisms is crucial for optimizing the design and operation of HAMR systems. Researchers are continuously exploring innovative approaches to enhance the heat transfer mechanisms in HAMR. This includes the development of advanced materials with improved thermal properties, the optimization of cooling systems, and the integration of novel heat sources. By improving the efficiency and control of heat transfer, HAMR technology can continue to advance, enabling higher areal density and improved data storage capabilities. In the next section, we will delve into the thermal stability and reliability considerations in HAMR, exploring the challenges and techniques for ensuring the long-term performance of HAMR systems. 4.3 Thermal stability and reliability. Thermal stability and reliability are crucial factors in the design and implementation of heat-assisted magnetic recording (HAMR) systems. As HAMR technology relies on localized heating to facilitate the writing process, it is essential to ensure that the thermal effects do not compromise the stability and reliability of the recording media and the overall system. 4.3.1 Thermal effects on recording media. One of the primary concerns in HAMR is the impact of elevated temperatures on the recording media. The localized heating during the writing process can lead to thermal fluctuations and induce changes in the magnetic properties of the media. These thermal effects can result in data corruption, reduced signal-to-noise ratio, and decreased overall reliability. To mitigate these thermal effects, extensive research has been conducted to develop recording media with enhanced thermal stability. The use of high-temperature resistant materials, such as heat-resistant alloys and multi-layer structures, has been explored to improve the thermal stability of the media. Additionally, the introduction of protective layers and thermal barriers can help minimize the impact of heat on the recording media. 4.3.2 Thermal stress and mechanical reliability. In HAMR systems, the localized heating can also induce thermal stress on the recording media and other components, which can lead to mechanical failures and reduced reliability. The repeated heating and cooling cycles can cause expansion and contraction of the materials, resulting in mechanical stress and potential damage. To address these challenges, careful consideration must be given to the mechanical design and material selection. The use of materials with low thermal expansion coefficients and high mechanical strength can help minimize the impact of thermal stress. Additionally, the implementation of thermal management techniques, such as heat sinks and thermal insulation, can help regulate the temperature and reduce the thermal stress on the components. 4.3.3 Aging and long-term reliability. Another aspect of thermal stability and reliability in HAMR systems is the long-term aging of the recording media and other components. Over time, the repeated exposure to elevated temperatures can lead to material degradation and changes in the magnetic properties, which can affect the long-term reliability and data integrity. To ensure long-term reliability, extensive testing and evaluation of the materials and components are necessary. Accelerated aging tests can be conducted to simulate the effects of prolonged exposure to elevated temperatures and assess the performance and reliability of the system over an extended period. Additionally, the development of advanced materials with improved thermal stability and resistance to aging can further enhance the long-term reliability of HAMR systems. 4.3.4 Environmental factors and reliability. In addition to thermal stability, the reliability of HAMR systems can also be influenced by environmental factors such as humidity, dust, and temperature variations. These factors can impact the performance and longevity of the recording media and other components, leading to potential data loss and system failures. To address these environmental challenges, proper encapsulation and sealing techniques can be employed to protect the sensitive components from moisture and dust. Additionally, temperature control mechanisms can be implemented to maintain a stable operating environment and minimize the impact of temperature variations on the system's reliability. 4.3.5 Reliability testing and evaluation. Reliability testing and evaluation play a crucial role in ensuring the robustness and durability of HAMR systems. Various testing methodologies, such as accelerated aging tests, thermal cycling tests, and environmental stress tests, can be employed to assess the system's reliability under different operating conditions. Reliability testing involves subjecting the system to extreme conditions and monitoring its performance and functionality over an extended period. This allows for the identification of potential weaknesses and vulnerabilities, enabling the development of mitigation strategies and improvements in the system design. 4.3.6 Reliability improvement techniques. To enhance the thermal stability and reliability of HAMR systems, several techniques can be employed. These include advanced thermal management, implementing efficient heat dissipation mechanisms, such as heat sinks and thermal insulation, to regulate the temperature and minimize thermal stress on the components. Material optimization, developing recording media and other components with improved thermal stability and resistance to aging, ensuring long-term reliability. Environmental protection, employing proper encapsulation and sealing techniques to protect the system from environmental factors such as humidity, dust, and temperature variations. Robust design, incorporating robust mechanical design principles and material selection to withstand thermal stress and ensure mechanical reliability. Quality control and testing, implementing stringent quality control measures and conducting thorough reliability testing and evaluation to identify and address potential weaknesses and vulnerabilities. By implementing these reliability improvement techniques, HAMR systems can achieve enhanced thermal stability and reliability, ensuring the integrity and longevity of the recorded data. In the next section, we will explore the various thermal management techniques employed in HAMR systems to regulate the temperature and optimize the performance of the system. 4.4 Thermal management techniques. Thermal management is a critical aspect of heat-assisted magnetic recording (HAMR) technology. As the name suggests, HAMR relies on the controlled application of heat to the recording medium to facilitate the writing of data. However, this heat can also have adverse effects on the overall performance and reliability of the system. Therefore, effective thermal management techniques are essential to ensure the proper functioning and longevity of HAMR systems. 4.4.1 Heat dissipation. One of the primary challenges in HAMR is efficiently dissipating the heat generated during the writing process. Excessive heat can lead to thermal instability, which can result in data corruption and reduced reliability. To address this issue, various heat dissipation techniques have been developed. 4.4.1.1 Heat sinks. Heat sinks are commonly used in HAMR systems to absorb and dissipate heat away from critical components. These devices typically consist of a thermally conductive material, such as copper or aluminum, with a large surface area to enhance heat transfer. Heat sinks are strategically placed in close proximity to the heat-generating components, such as the laser or the write head, to effectively remove excess heat. 4.4.1.2 Thermal interface materials. Thermal interface materials (TIMs) play a crucial role in facilitating heat transfer between different components in HAMR systems. TIMs are placed between the heat source and the heat sink to minimize thermal resistance and improve heat dissipation. Commonly used TIMs include thermal greases, thermal pads, and phase change materials. These materials help to fill in microscopic gaps and irregularities between the surfaces, ensuring efficient heat transfer. 4.4.2 Active cooling techniques. In addition to passive heat dissipation methods, active cooling techniques are also employed in HAMR systems to further enhance thermal management. Active cooling involves the use of external devices or mechanisms to actively remove heat from the system. 4.4.2.1 Fans and heat exchangers. Fans and heat exchangers are commonly used in HAMR systems to provide active cooling. Fans circulate air around the components, facilitating heat transfer and reducing the overall temperature. Heat exchangers, on the other hand, use a fluid medium, such as water or refrigerant, to absorb heat from the system and dissipate it elsewhere. These active cooling techniques are particularly effective in high-power HAMR systems where passive cooling alone may not be sufficient. 4.4.2.2 Thermoelectric cooling. Thermoelectric cooling is another active cooling technique that can be employed in HAMR systems. It utilizes the Peltier effect, which is the phenomenon of heat absorption or release at the junction of two dissimilar materials when an electric current is passed through them. Thermoelectric coolers consist of multiple thermoelectric modules that can actively cool specific components by absorbing heat from one side and dissipating it on the other side. 4.4.3 Thermal design considerations. Effective thermal management in HAMR systems requires careful consideration of various design aspects. These considerations aim to optimize heat dissipation and minimize thermal effects on the system. 4.4.3.1 Component placement and layout. The placement and layout of components within the HAMR system can significantly impact thermal management. By strategically positioning heat-generating components, such as the laser and right head, in relation to heat sinks and cooling mechanisms, heat dissipation can be maximized. Additionally, proper spacing between components can help prevent heat buildup and ensure efficient airflow. 4.4.3.2 Material selection. The choice of materials used in the construction of HAMR systems can also influence thermal management. Optimal material selection can enhance heat transfer and reduce thermal resistance. For example, using thermally conductive materials for heat sinks and thermal interface materials can improve overall heat dissipation. 4.4.3.3 System integration. Integrating thermal management techniques into the overall system design is crucial for effective heat dissipation. This involves considering the placement and routing of cooling channels, optimizing the flow of cooling fluids, and ensuring proper contact between heat-generating components and heat sinks or thermal interface materials. System integration plays a vital role in maximizing the efficiency of thermal management techniques. 4.4.4 Advanced thermal management techniques. As HAMR technology continues to evolve, researchers are exploring advanced thermal management techniques to further improve heat dissipation and system reliability. 4.4.4.1 Microchannel cooling. Microchannel cooling involves the use of micro-sized channels embedded within the HAMR system to enhance heat transfer. These channels provide a large surface area for heat exchange and can be designed to optimize fluid flow and heat dissipation. Microchannel cooling offers the potential for highly efficient thermal management in HAMR systems. 4.4.4.2 Phase change materials. Phase change materials (PCMs) are substances that can absorb and release large amounts of heat during phase transitions. In HAMR systems, PCMs can be used to store and dissipate excess heat generated during the writing process. By utilizing the latent heat of fusion or vaporization, PCMs can effectively regulate the temperature and prevent thermal instability. In conclusion, thermal management techniques play a crucial role in ensuring the reliable and efficient operation of heat-assisted magnetic recording systems. Effective heat dissipation, active cooling methods, and careful design considerations are essential to minimize thermal effects and optimize the performance of HAMR technology. As the field continues to advance, the exploration of advanced thermal management techniques holds the promise of further enhancing the capabilities and reliability of HAMR systems. 5. Nanoparticles and plasmonics in heat-assisted magnetic recording. 5.1 Introduction to nanoparticles and plasmonics. In recent years, the field of heat-assisted magnetic recording (HAMR) has gained significant attention as a promising technology for achieving higher areal densities in magnetic storage devices. One of the key components in HAMR is the use of nanoparticles and plasmonics, which play a crucial role in enhancing the efficiency and performance of the recording process. 5.1.1 Nanoparticles in heat-assisted magnetic recording. Nanoparticles, as the name suggests, are extremely small particles with dimensions typically ranging from 1 to 100 nanometers. These particles exhibit unique physical and chemical properties that differ from their bulk counterparts. In the context of HAMR, nanoparticles are used to enhance the absorption of light and facilitate the localized heating of the recording media. The choice of nanoparticles is critical in HAMR systems as they need to possess specific properties to effectively convert light energy into heat. One of the most commonly used nanoparticles in HAMR is gold nanoparticles. Gold nanoparticles have excellent plasmonic properties, which means they can efficiently absorb and scatter light at specific wavelengths. This property makes them ideal for enhancing the absorption of the laser light used in HAMR systems. Other types of nanoparticles, such as silver Ag and aluminum Al, have also been explored for their plasmonic properties in HAMR. These nanoparticles can be tailored to absorb light at different wavelengths, allowing for optimization of the heating process. Additionally, magnetic nanoparticles, such as iron oxide Fe3O4 nanoparticles, have been investigated for their potential to enhance the magnetic properties of the recording media. 5.1.2 Plasmonics in heat-assisted magnetic recording. Plasmonics is a branch of nanophotonics that deals with the interaction between light and metallic nanostructures, particularly plasmonic nanoparticles. Plasmonic nanoparticles exhibit a phenomenon called localized surface plasmon resonance, LSPR, which occurs when the collective oscillation of electrons in the nanoparticle is excited by incident light. In the context of HAMR, plasmonics plays a crucial role in enhancing the absorption of light and generating localized heating. When plasmonic nanoparticles are illuminated with light at their resonance wavelength, the incident photons couple with the collective oscillation of electrons, resulting in a significant enhancement of the local electromagnetic field. This enhanced field leads to a higher absorption of light by the nanoparticles, which in turn increases the efficiency of the heating process. The localized heating generated by plasmonic nanoparticles is essential for HAMR because it enables the precise and controlled switching of the magnetic domains in the recording media. By focusing the heat on a small region, the coercivity of the media can be reduced, allowing for easier magnetization reversal. This localized heating also helps to minimize the thermal impact on the surrounding areas, ensuring the stability and reliability of the recording process. 5.1.3 Nanoparticle Media Interactions. The interaction between nanoparticles and the recording media is a critical aspect of HAMR. When nanoparticles are deposited on the surface of the media, they can affect the magnetic properties and thermal behavior of the recording layer. The proximity of the nanoparticles to the media can influence the heat transfer process and the efficiency of the localized heating. One of the key challenges in nanoparticle media interactions is achieving a uniform and controlled distribution of nanoparticles on the media surface. The deposition techniques, such as physical vapor deposition (PVD) and chemical vapor deposition (CVD), play a crucial role in determining the nanoparticle density and distribution. The size, shape, and composition of the nanoparticles also affect their interaction with the media. The presence of nanoparticles can modify the magnetic properties of the recording media. For example, the exchange coupling between the nanoparticles and the media can lead to changes in the coercivity and remanence of the media. This interaction can be both beneficial and detrimental, depending on the specific application and design requirements. 5.1.4 Applications and Future Directions. The use of nanoparticles and plasmonics in HAMR has opened up new possibilities for achieving higher areal densities in magnetic storage devices. The ability to precisely control the heating process and enhance the magnetic properties of the recording media has the potential to revolutionize the field of data storage. One of the key applications of HAMR is in the development of high-capacity hard disk drives, HDDs. By utilizing nanoparticles and plasmonics, HDDs can achieve areal densities beyond the limitations of conventional magnetic recording technologies. This enables the storage of larger amounts of data in smaller form factors, leading to more compact and efficient storage solutions. In addition to HDDs, HAMR has the potential to be applied in other areas such as magnetic random access memory (MRAM) and magnetic sensors. The precise control of the magnetic properties and the ability to switch magnetic domains at high speeds make HAMR an attractive technology for these applications. Looking ahead, further research and development are needed to optimize the performance and reliability of nanoparticles and plasmonics in HAMR systems. The design and synthesis of nanoparticles with tailored properties, as well as the development of advanced deposition techniques, will be crucial in realizing the full potential of this technology. In conclusion, nanoparticles and plasmonics play a vital role in enhancing the efficiency and performance of heat-assisted magnetic recording. The ability to control the heating process and modify the magnetic properties of the recording media opens up new possibilities for achieving higher areal densities in magnetic storage devices. With ongoing research and development, the future of HAMR looks promising, paving the way for more advanced and compact data storage solutions. 5.2 Plasmonic nanoparticles for heat-assisted magnetic recording. Plasmonic nanoparticles have emerged as a promising tool in the field of heat-assisted magnetic recording, HAMR. These nanoparticles, typically made of noble metals such as gold or silver, exhibit unique optical properties that can be harnessed to enhance the efficiency and reliability of HAMR systems. In this section, we will explore the role of plasmonic nanoparticles in HAMR and discuss their potential applications and future directions. 5.2.1 Plasmonic resonance and near-field enhancement. Plasmonic nanoparticles owe their unique properties to the phenomenon known as plasmon resonance. When illuminated with light of a specific wavelength, these nanoparticles can resonate and concentrate the electromagnetic field in their vicinity. This localized enhancement of the electromagnetic field, known as the near field, can be utilized to achieve precise and localized heating in HAMR systems. In the context of HAMR, plasmonic nanoparticles can be integrated into the recording media or the write head to enhance the heating process. By carefully engineering the size, shape, and composition of these nanoparticles, their plasmon resonance can be tuned to match the wavelength of the incident light used for heating. This allows for efficient absorption of light energy and subsequent conversion into heat, which is crucial for achieving the necessary temperature increase in the recording media. 5.2.2 Enhanced light absorption and heat generation. One of the key advantages of using plasmonic nanoparticles in HAMR is their ability to enhance light absorption in the recording media. Traditional HAMR systems rely on the use of a laser to heat the recording media, but a significant portion of the incident light is reflected or transmitted, resulting in energy loss. By incorporating plasmonic nanoparticles into the recording media, the absorption of light can be significantly increased due to the near-field enhancement effect. The localized heating provided by plasmonic nanoparticles allows for precise control over the temperature distribution in the recording media. This is particularly important in HAMR, as the magnetic properties of the recording media are highly temperature-dependent. By achieving a more uniform and controlled temperature profile, the stability and reliability of the recorded data can be improved. 5.2.3 Plasmonic nanoparticle media interactions. The interaction between plasmonic nanoparticles and the recording media is a complex phenomenon that involves various physical processes. When plasmonic nanoparticles are integrated into the recording media, they can interact with the magnetic grains and affect their thermal properties. This interaction can lead to changes in the coercivity, remanence, and thermal stability of the recording media. Furthermore, the presence of plasmonic nanoparticles can also influence the magnetic field distribution during the writing process. The near-field enhancement effect can modify the local magnetic field strength, which in turn affects the writing efficiency and the quality of the recorded data. Understanding and optimizing these nanoparticle media interactions is crucial for achieving high-performance HAMR systems. 5.2.4 Applications and future directions. The integration of plasmonic nanoparticles into HAMR systems opens up a wide range of potential applications. One of the key areas of interest is the development of high-density magnetic storage devices. By leveraging the near-field enhancement effect provided by plasmonic nanoparticles, it is possible to achieve higher areal densities and increased data storage capacities. Another promising application is the development of ultra-fast magnetic recording systems. The localized heating provided by plasmonic nanoparticles enables rapid and precise switching of the magnetic domains, leading to faster writing speeds and improved data transfer rates. This can have significant implications for various industries, such as data centers, cloud computing, and high-performance computing. In terms of future directions, ongoing research is focused on further improving the efficiency and reliability of plasmonic nanoparticles in HAMR systems. This includes exploring new materials, optimizing the nanoparticle design, and developing novel fabrication techniques. Additionally, efforts are being made to better understand the fundamental physics behind plasmonic nanoparticle media interactions and to develop advanced modeling and simulation tools for HAMR system design. In conclusion, plasmonic nanoparticles offer exciting opportunities for enhancing the performance of HAMR systems. Their unique optical properties and near-field enhancement effect enable efficient light absorption and precise heating in the recording media. By carefully engineering the nanoparticle properties and optimizing their integration into HAMR systems, it is possible to achieve higher areal densities, faster writing speeds, and improved data storage capabilities. Continued research and development in this field hold great promise for the future of magnetic recording technology. 5.3 Nanoparticle media interactions. In heat-assisted magnetic recording, HAMR, the interaction between nanoparticles and the recording media plays a crucial role in achieving high-density data storage. Nanoparticles, specifically plasmonic nanoparticles, are used to enhance the heating efficiency and control the localized heating in HAMR systems. This section will explore the various aspects of nanoparticle media interactions in HAMR and their impact on the recording process. 5.3.1 Plasmonic nanoparticles in HAMR. Plasmonic nanoparticles, such as gold or silver nanoparticles, have unique optical properties that make them ideal for HAMR applications. These nanoparticles can efficiently absorb and convert light energy into heat due to their localized surface plasmon resonance (LSPR) effect. The LSPR effect occurs when the incident light matches the natural frequency of the nanoparticles' collective electron oscillations, resulting in a strong electromagnetic field enhancement and heat generation. In HAMR, plasmonic nanoparticles are typically integrated into the recording media to enhance the heating efficiency. The nanoparticles are dispersed within a thin layer of the recording media, forming a nanoparticle doped layer. When the laser is focused on the media, the plasmonic nanoparticles absorb the incident light, converting it into heat and raising the temperature of the surrounding media. This localized heating enables the recording of data at high densities. 5.3.2 Heat transfer mechanisms. The interaction between plasmonic nanoparticles and the recording media involves several heat transfer mechanisms. The primary mechanism is the transfer of heat from the nanoparticles to the media through conduction. As the nanoparticles absorb light and heat up, the thermal energy is transferred to the surrounding media, causing a localized temperature increase. This temperature rise facilitates the switching of the magnetic domains in the media, allowing for data recording. Another heat transfer mechanism is the transfer of heat from the nanoparticles to the media through radiation. When the nanoparticles are heated, they emit thermal radiation in the form of photons. These photons can be absorbed by the media, further increasing its temperature. The radiation heat transfer mechanism is particularly important when the nanoparticles are in close proximity to the media, as it enables efficient heat transfer. 5.3.3 Nanoparticle media interactions. The interaction between nanoparticles and the recording media in HAMR involves several key processes. Firstly, the absorption of light by the plasmonic nanoparticles leads to the generation of localized heat. The efficiency of this process depends on the size, shape, and composition of the nanoparticles, as well as the wavelength of the incident light. By carefully selecting the properties of the nanoparticles, researchers can optimize the heating efficiency and achieve precise control over the temperature distribution in the media. Secondly, the heat generated by the nanoparticles is transferred to the recording media, causing a localized temperature increase. This temperature rise is critical for achieving the Curie temperature of the media, which allows for the switching of magnetic domains and data recording. The efficiency of heat transfer depends on factors such as the proximity of the nanoparticles to the media, the thermal conductivity of the media, and the heat transfer mechanisms involved. Furthermore, the interaction between nanoparticles and the media can also affect the magnetic properties of the media. The presence of nanoparticles can alter the magnetic anisotropy and coercivity of the media, influencing its ability to retain magnetization and store data. Researchers are actively studying the nanoparticle media interactions to understand and optimize these effects for improved recording performance. 5.3.4 Challenges and Future Directions. While nanoparticle media interactions offer significant potential for enhancing HAMR technology, there are several challenges that need to be addressed. One challenge is the stability and reliability of the nanoparticles within the recording media. Over time, nanoparticles may agglomerate or migrate, leading to changes in their optical and thermal properties. Ensuring the long-term stability of nanoparticles is crucial for maintaining consistent heating performance in HAMR systems. Another challenge is the optimization of nanoparticle properties for specific media materials. Different recording media have varying thermal and magnetic properties, requiring tailored nanoparticle designs to achieve optimal heating and recording performance. Researchers are exploring various nanoparticle compositions, sizes, and shapes to find the most suitable configurations for different media materials. In the future, advancements in nanofabrication techniques and material science will enable the development of more sophisticated nanoparticles with enhanced properties. Additionally, the integration of other nanomaterials, such as magnetic nanoparticles, into the recording media may further improve the performance of HAMR systems. Continued research and development in nanoparticle media interactions will pave the way for higher density data storage and the realization of the full potential of HAMR technology. Conclusion. The interaction between nanoparticles and the recording media is a critical aspect of heat-assisted magnetic recording (HAMR) technology. Plasmonic nanoparticles, with their unique optical properties, enable efficient localized heating in HAMR systems. The heat transfer mechanisms between nanoparticles and the media, such as conduction and radiation, play a crucial role in achieving the desired temperature rise for data recording. Understanding and optimizing nanoparticle media interactions are essential for improving the performance and reliability of HAMR systems. Future advancements in nanoparticle design and fabrication techniques will further enhance the capabilities of HAMR technology, enabling higher density data storage and opening up new possibilities for data-intensive applications. 5.4 Applications and Future Directions. Heat-assisted magnetic recording (HAMR) technology has the potential to revolutionize the field of magnetic recording by enabling higher data storage densities and improved data reliability. In this section, we will explore the current applications of HAMR and discuss the future directions and research challenges in this exciting field. 5.4.1 Current Applications of Heat-Assisted Magnetic Recording. Currently, HAMR technology is primarily being developed for high-capacity hard disk drives (HDDs). The ability of HAMR to increase the areal density of HDDs makes it an ideal solution for data-intensive applications such as cloud storage, big data analytics, and video streaming. With the exponential growth of data in these fields, there is a pressing need for higher capacity storage solutions, and HAMR offers a promising solution. HAMR technology also has potential applications in other areas such as archival storage, data centers, and enterprise storage systems. Archival storage requires long-term data retention and reliability, and HAMR's ability to increase the storage density can significantly reduce the physical footprint and cost of archival systems. Data centers and enterprise storage systems can benefit from HAMR's increased capacity, allowing for more efficient data management and reduced infrastructure costs. 5.4.2 Emerging Applications and Opportunities. While HAMR is primarily being developed for HDDs, there are emerging applications and opportunities that could benefit from this technology. One such application is in the field of magnetic random access memory (MRAM). MRAM is a non-volatile memory technology that combines the benefits of both traditional magnetic storage and semiconductor-based memory. HAMR could potentially enhance the storage density and performance of MRAM, making it a more viable alternative to other memory technologies such as flash memory. Another emerging application is in the field of magnetic sensors. HAMR technology can be used to create highly sensitive and compact magnetic sensors for various applications, including biomedical sensing, automotive sensors, and industrial monitoring. The increased storage density and improved data reliability of HAMR can enable the development of more advanced and efficient magnetic sensor systems. Furthermore, HAMR technology can also find applications in the field of data storage for consumer electronics. With the increasing demand for high-capacity storage in smartphones, tablets, and wearable devices, HAMR can provide a solution to meet these storage requirements. The compact size and high storage density of HAMR can enable manufacturers to produce smaller and more powerful devices without compromising on storage capacity. 5.4.3 Future Directions and Research Challenges. As HAMR technology continues to evolve, there are several research challenges and future directions that need to be addressed. One of the key challenges is the development of more efficient and reliable heat sources. Current heat sources, such as lasers and near-field optical heating, have limitations in terms of power consumption, scalability, and reliability. Research efforts are focused on developing new heat sources that can provide precise and controlled heating while minimizing energy consumption and improving reliability. Another research direction is the development of advanced magnetic materials specifically designed for HAMR. The magnetic materials used in HAMR must exhibit high magnetic anisotropy, thermal stability, and compatibility with the heat sources. Researchers are exploring new materials and material combinations to optimize the performance and reliability of HAMR systems. Thermal management is another important area of research in HAMR technology. As the heat generated during the recording process can affect the stability and reliability of the storage media, effective thermal management techniques are required to dissipate the heat and maintain the desired operating temperature. Researchers are investigating various cooling methods, such as heat sinks and thermoelectric cooling, to improve the thermal management of HAMR systems. Furthermore, the integration of HAMR technology into existing manufacturing processes and infrastructure is a significant challenge. The manufacturing processes for HAMR systems need to be optimized to ensure high yield and cost-effective production. Integration challenges, such as the alignment of the right head with the storage media and the control of the heat source, also need to be addressed to enable the mass production of HAMR-based storage devices. In conclusion, HAMR technology holds great promise for the future of magnetic recording. Its ability to increase storage density and improve data reliability makes it an ideal solution for a wide range of applications, including high-capacity HDDs, archival storage, data centers, and consumer electronics. However, there are still several research challenges that need to be overcome to fully realize the potential of HAMR. Continued research and development efforts in areas such as heat sources, magnetic materials, thermal management, and manufacturing processes will pave the way for the widespread adoption of HAMR technology in the coming years. 6. Recording media for heat-assisted magnetic recording. 6.1 Introduction to recording media. Recording media is a crucial component in heat-assisted magnetic recording (HAMR) technology. It plays a vital role in storing and retrieving data in magnetic storage devices such as hard disk drives (HDDs). In this section, we will explore the fundamentals of recording media, its characteristics, and its advancements in the context of HAMR. 6.1.1 Magnetic Storage Basics. Before delving into the specifics of recording media, let's first understand the basics of magnetic storage. In traditional magnetic recording, data is stored as magnetic patterns on a thin film of magnetic material. These patterns represent binary information, with each bit being magnetized in either a 0 or 1 state. The magnetic material used in recording media is typically a ferromagnetic material, such as iron, cobalt, or nickel, or a combination of these elements. These materials possess unique magnetic properties that allow them to retain their magnetization even in the absence of an external magnetic field. 6.1.2 Magnetic recording media for HAMR. In HAMR technology, the recording media is specifically designed to withstand the high temperatures generated by the heat source, typically a laser. The recording media must exhibit excellent thermal stability and reliability to ensure that the recorded data remains intact over time. One of the key requirements for HAMR recording media is a high Curie temperature. The Curie temperature is the temperature at which a magnetic material loses its ferromagnetic properties and becomes paramagnetic. By selecting a recording media with a high Curie temperature, the data can be stored at higher densities without the risk of losing magnetization due to thermal fluctuations. Another important characteristic of HAMR recording media is its magnetic anisotropy. Magnetic anisotropy refers to the preferred direction of magnetization in a material. In HAMR, the recording media is typically designed to have a perpendicular magnetic anisotropy, PMA, where the magnetization is oriented perpendicular to the surface of the media. PMA allows for higher areal densities and improved thermal stability compared to materials with in-plane magnetic anisotropy. 6.1.3 Advancements in recording media for HAMR. Over the years, significant advancements have been made in the development of recording media for HAMR. Researchers and engineers have focused on improving the thermal stability, writability, and reliability of the media to enable higher data storage densities and faster data transfer rates. One approach to enhancing the thermal stability of recording media is through the use of multi-layer structures. By stacking multiple layers of different magnetic materials with varying Curie temperatures, the overall thermal stability of the media can be improved. This allows for more precise control of the magnetization and reduces the risk of data loss due to thermal fluctuations. Another area of research is the development of novel magnetic materials with enhanced magnetic properties. For example, the use of rare earth magnets, such as neodymium iron boron (NFeB), has shown promise in improving the magnetic performance of recording media. These materials exhibit high magnetic anisotropy and saturation magnetization, making them suitable for high-density data storage applications. Furthermore, advancements in nanotechnology have opened up new possibilities for recording media design. The integration of nanoparticles into the recording media can enhance its magnetic properties and improve writability. Plasmonic nanoparticles, which can interact with light and generate localized heat, have also been explored for their potential in HAMR. These nanoparticles can be used to assist in the heating process, enabling more precise control over the magnetization of the media. 6.1.4 Media Design Considerations. When designing recording media for HAMR, several factors need to be considered. One of the primary considerations is the trade-off between thermal stability and writability. While high thermal stability is desirable for data retention, it can also make it more challenging to write data onto the media. Finding the right balance between these two factors is crucial to ensure optimal performance. Another consideration is the compatibility of the recording media with the write head. The write head generates the magnetic field necessary to write data onto the media. The recording media must be designed to interact effectively with the write head, allowing for efficient data recording and retrieval. Additionally, the durability and reliability of the recording media are essential for long-term data storage. The media should be resistant to wear and corrosion to ensure the integrity of the stored data over time. Extensive testing and evaluation are conducted to assess the reliability of the media under various operating conditions and to identify any potential failure mechanisms. In conclusion, recording media is a critical component in HAMR technology, enabling high-density data storage and faster data transfer rates. The development of recording media with improved thermal stability, magnetic properties, and durability has been instrumental in advancing HAMR technology. Ongoing research and development efforts continue to push the boundaries of recording media design, paving the way for future advancements in magnetic storage technology. 6.2 Magnetic recording media for heat-assisted magnetic recording. Magnetic recording media is a crucial component in heat-assisted magnetic recording (HAMR) technology. It plays a vital role in storing and retrieving data in HAMR systems. The development of suitable recording media is essential to achieve high-density data storage and improve the overall performance of HAMR. 6.2.1 Magnetic properties of recording media. The magnetic properties of recording media are of utmost importance in HAMR. The media should possess high magnetic anisotropy, which determines the stability of the recorded data. High anisotropy ensures that the recorded information remains intact even at elevated temperatures during the writing process. Additionally, the media should exhibit a high coercivity, which is the ability to resist changes in magnetization. This property is crucial for maintaining the stability of the recorded data over time. In HAMR, the recording media is typically composed of a thin magnetic layer, such as iron platinum (FePt) or iron palladium (FePd) alloy, deposited on a non-magnetic substrate. These materials have been extensively studied and optimized for their magnetic properties to meet the requirements of HAMR technology. The use of these materials allows for high thermal stability and excellent magnetic recording performance. 6.2.2 Media Design Considerations. The design of the recording media in HAMR involves several considerations to ensure optimal performance. One important aspect is the thickness of the magnetic layer. The thickness should be carefully chosen to achieve the desired magnetic properties, such as high coercivity and anisotropy. A thicker magnetic layer can provide higher thermal stability but may also increase the switching field, making it more challenging to write data. On the other hand, a thinner magnetic layer may have lower thermal stability but can facilitate easier writing. Another consideration is the grain size of the magnetic layer. Smaller grain sizes are desirable as they allow for higher areal density and improved thermal stability. However, reducing the grain size can also lead to increased magnetic noise, which can degrade the signal-to-noise ratio and affect the readback performance. Therefore, a balance needs to be struck between grain size and thermal stability to optimize the performance of the recording media. The choice of the non-magnetic substrate is also crucial in media design. The substrate should have low thermal conductivity to minimize heat dissipation during the writing process. This ensures that the heat generated by the heat source is effectively transferred to the magnetic layer, enabling efficient writing. Additionally, the substrate should have good mechanical properties to provide stability and durability to the recording media. 6.2.3 Advancements in recording media for HAMR. Significant advancements have been made in the development of recording media for HAMR. Researchers have focused on improving the magnetic properties of the media to achieve higher areal density and enhanced thermal stability. One approach is the use of multi-layer structures, where different magnetic layers with varying properties are stacked on top of each other. This allows for fine-tuning of the magnetic properties and enables better control over the writing process. Another area of research is the exploration of new magnetic materials for recording media. For example, researchers have investigated the use of rare earth transition metal alloys, such as gadolinium iron cobalt (GDFECO), which exhibit high magnetic anisotropy and excellent thermal stability. These materials show promise in achieving even higher areal density and improved performance in HAMR systems. Furthermore, advancements in nanotechnology have opened up new possibilities for recording media design. The integration of nanoparticles into the magnetic layer has shown potential in enhancing the magnetic properties and thermal stability of the media. The presence of nanoparticles can modify the magnetic interactions within the media, leading to improved recording performance. 6.2.4 Challenges and Future Directions. Despite the significant progress in recording media for HAMR, several challenges remain. One challenge is the thermal stability of the media at high temperatures. As the areal density increases, the thermal stability requirements become more stringent. Researchers are actively working on developing new materials and structures that can withstand higher temperatures without compromising the stability of the recorded data. Another challenge is the trade-off between thermal stability and writability. Increasing the thermal stability of the media often leads to higher switching fields, making it more challenging to write data. Finding the right balance between these conflicting requirements is crucial for achieving optimal performance in HAMR systems. In the future, the development of novel materials and advanced fabrication techniques will continue to drive advancements in recording media for HAMR. The integration of emerging technologies, such as plasmonics and nanophotonics, may also play a significant role in enhancing the performance of the media. These technologies can enable precise control over the heat generation and transfer processes, leading to improved writability and thermal stability. In conclusion, the design and development of recording media for HAMR are critical for achieving high-density data storage and improving the performance of HAMR systems. The magnetic properties, media design considerations, advancements, and challenges discussed in this section highlight the ongoing efforts to optimize recording media for HAMR. Continued research and innovation in this field will pave the way for the future of heat-assisted magnetic recording. 6.3 Advancements in recording media for heat-assisted magnetic recording. Heat-assisted magnetic recording (HAMR) technology has revolutionized the field of magnetic recording by enabling higher areal densities and increased storage capacities. The recording media used in HAMR plays a crucial role in achieving these advancements. In this section, we will explore the recent advancements in recording media for HAMR and their impact on the performance and reliability of the technology. 6.3.1 High anisotropy recording media. One of the key requirements for HAMR is the use of recording media with high magnetic anisotropy. High anisotropy materials allow for stable and reliable recording of data at high areal densities. Over the years, significant advancements have been made in developing recording media with enhanced anisotropy. Researchers have explored various materials, such as Fe-PT, L10 Fe-PT, and COPT, which exhibit high magnetic anisotropy. These materials have shown promising results in terms of thermal stability and writability. Additionally, the use of multilayer structures, such as Fe-PT-C, has been investigated to further enhance the anisotropy and thermal stability of the recording media. Furthermore, the introduction of exchange-coupled composite (ECC) media has shown great potential for HAMR applications. ECC media consist of a soft magnetic layer coupled with a hard magnetic layer, providing a balance between writability and thermal stability. This advancement has opened up new possibilities for achieving higher areal densities in HAMR systems. 6.3.2 Grain segregation and isolation techniques. To achieve high areal densities in HAMR, it is essential to minimize the grain size of the recording media. Smaller grain sizes allow for tighter packing of magnetic domains, resulting in increased storage capacity. However, reducing the grain size also leads to increased thermal instability and susceptibility to thermal fluctuations. To overcome this challenge, researchers have developed grain segregation and isolation techniques. These techniques involve the use of thin interlayers or grain isolation layers to separate the magnetic grains and prevent their interaction. By isolating the grains, the thermal stability of the recording media can be improved without compromising the areal density. Various materials, such as CO2, MgO, and TO2, have been explored as grain isolation layers. These materials provide a barrier between the magnetic grains, reducing the intergranular exchange coupling and improving the thermal stability of the media. Additionally, the use of interlayers, such as RU, has been found to enhance the segregation of grains, further improving the performance of HAMR media. 6.3.3 Hybrid recording media. Hybrid recording media have emerged as a promising approach to overcome the limitations of conventional magnetic recording media. These media combine the advantages of different materials to achieve enhanced writability, thermal stability, and areal density. One such example is the use of exchange-coupled composite (ECC) media with a granular structure. ECC media consist of a soft magnetic layer and a hard magnetic layer, where the exchange coupling between the layers provides writability, while the hard magnetic layer ensures thermal stability. This hybrid approach allows for a balance between writability and thermal stability, enabling higher areal densities in HAMR systems. Another approach is the use of hybrid media with a combination of magnetic and non-magnetic layers. The non-magnetic layers act as thermal barriers, reducing the heat transfer to the magnetic layer during the writing process. This reduces the thermal fluctuations and improves the thermal stability of the media. By carefully designing the composition and thickness of the non-magnetic layers, the performance of HAMR media can be significantly enhanced. 6.3.4 Surface modification techniques. Surface modification techniques have gained significant attention in recent years for improving the performance of HAMR media. These techniques involve the modification of the surface properties of the recording media to enhance writability, thermal stability, and signal-to-noise ratio. One such technique is the use of surface plasmon resonance (SPR) to enhance the absorption of the incident laser light. By depositing plasmonic nanoparticles on the surface of the media, the localized surface plasmon resonance can be excited, leading to enhanced absorption and localized heating. This technique improves the writability of the media by reducing the laser power required for writing. Additionally, surface modification techniques, such as ion implantation and ion beam irradiation, have been explored to tailor the surface properties of the recording media. These techniques can modify the magnetic properties, crystal structure, and surface roughness, resulting in improved writability and thermal stability. 6.3.5 Future directions in recording media for HAMR. The advancements in recording media for HAMR have paved the way for higher areal densities and increased storage capacities. However, there are still several challenges that need to be addressed to further improve the performance and reliability of HAMR systems. Future research in recording media for HAMR will focus on developing materials with even higher magnetic anisotropy and thermal stability. The exploration of novel materials, such as rare earth magnets and magnetic alloys, holds great promise for achieving these goals. Additionally, the development of advanced surface modification techniques and hybrid media structures will continue to play a crucial role in enhancing the performance of HAMR systems. Furthermore, the integration of recording media with other components, such as write heads and signal processing circuits, will be a key area of research. The optimization of the interface between the recording media and other components will be essential for achieving reliable and high-performance HAMR systems. In conclusion, the advancements in recording media for HAMR have significantly contributed to the progress of this technology. The development of high anisotropy media, grain segregation techniques, hybrid media structures, surface modification techniques, and future research directions will continue to shape the future of HAMR and enable the realization of even higher areal densities and increased storage capacities. 6.4 Media design considerations. In heat-assisted magnetic recording (HAMR), the design of the recording media plays a crucial role in achieving high-density data storage and reliable data retrieval. The media design considerations encompass various aspects, including the magnetic properties, thermal stability, and material composition. This section explores the key factors that need to be taken into account when designing the recording media for HAMR systems. 6.4.1 Magnetic properties. The magnetic properties of the recording media are of utmost importance in HAMR technology. The media should exhibit high magnetic coercivity, which refers to the ability of the material to resist changes in its magnetization. A high coercivity ensures that the recorded data remains stable over time and is not easily affected by external magnetic fields or thermal fluctuations. Additionally, the media should possess a high magnetic saturation, which is the maximum magnetization that can be achieved in the material. This property allows for a larger signal-to-noise ratio during data readout, resulting in improved data reliability. The magnetic anisotropy, which determines the preferred direction of magnetization in the media, should also be carefully considered to ensure efficient writing and reading of data. To achieve these desired magnetic properties, various materials have been explored for HAMR media, including iron-platinum (FePt) alloys, cobalt-platinum (COPT) alloys, and rare earth transition metal (ReTM) alloys. These materials exhibit high coercivity and magnetic saturation, making them suitable candidates for HAMR applications. 6.4.2 Thermal stability. Thermal stability is another critical aspect to consider in media design for HAMR. The recording media should be able to withstand the high temperatures generated during the writing process without undergoing significant changes in its magnetic properties. This ensures that the recorded data remains stable and can be reliably read back. One approach to enhance the thermal stability of the media is to incorporate a thin layer of a thermally stable material, such as tantalum top, between the recording layer and the substrate. This layer acts as a thermal barrier, preventing excessive heat from reaching the substrate and affecting its magnetic properties. The use of such thermal barriers has been shown to improve the thermal stability of HAMR media. Another consideration is the grain size of the recording media. Smaller grain sizes have been found to enhance the thermal stability of the media by reducing the likelihood of thermally induced magnetic fluctuations. Therefore, media design should aim to achieve a fine grain structure to ensure optimal thermal stability. 6.4.3 Material composition. The material composition of the recording media is a crucial factor in determining its magnetic and thermal properties. The choice of materials and their composition can significantly impact the performance and reliability of HAMR systems. One approach to improve the magnetic properties of the media is to introduce alloying elements. For example, the addition of platinum point to iron Fe in FePt alloys enhances the magnetic anisotropy and coercivity of the media. Similarly, the addition of cobalt Co to platinum point in COPT alloys improves the magnetic properties. The composition of the media also affects its thermal properties. For instance, the addition of a thermally conductive material, such as copper Cu, to the recording layer can enhance the heat dissipation during the writing process, reducing the risk of thermal damage to the media. Furthermore, the material composition can influence the grain size and grain boundary properties of the media, which in turn affect the thermal stability and magnetic performance. Therefore, careful consideration should be given to the selection and composition of materials to optimize the overall performance of the recording media. 6.4.4 Surface roughness and smoothness. The surface roughness and smoothness of the recording media are critical factors that can impact the writability and readback performance in HAMR systems. A smooth and uniform surface is essential for achieving precise and reliable writing of data. Excessive surface roughness can lead to variations in the heat distribution during the writing process, resulting in inconsistent data recording. It can also cause increased friction between the write head and the media, leading to wear and reduced durability. To ensure a smooth and uniform surface, various techniques, such as chemical mechanical polishing, CMP, and ion beam etching, can be employed during the manufacturing process. These techniques help to reduce surface roughness and improve the overall performance of the recording media. 6.4.5 Lubricant layer. In HAMR systems, a lubricant layer is typically applied on top of the recording media to reduce friction and wear between the write head and the media. The lubricant layer acts as a protective barrier, preventing direct contact between the write head and the media surface. The choice of lubricant material and its thickness is crucial in media design. The lubricant should have low volatility and good thermal stability to withstand the high temperatures generated during the writing process. It should also exhibit good adhesion to the media surface to ensure long-term durability. Additionally, the lubricant layer should have a uniform thickness across the media surface to ensure consistent performance. Variations in lubricant thickness can lead to variations in the flying height of the write head, affecting the writing and readback performance. Overall, the design of the recording media for HAMR systems requires careful consideration of various factors, including magnetic properties, thermal stability, material composition, surface roughness, and lubricant layer. By optimizing these design considerations, it is possible to achieve high-density data storage and reliable data retrieval in HAMR technology. 7. Write heads for heat-assisted magnetic recording. 7.1 Introduction to write heads. In heat-assisted magnetic recording, HAMR, the write head plays a crucial role in the recording process. It is responsible for generating the necessary magnetic field to write data onto the recording media. The write head consists of several components that work together to achieve precise and efficient data recording. 7.1.1 Components of a write head. A typical write head in HAMR consists of the following components. 1. Pole tip. The pole tip is the part of the write head that comes into direct contact with the recording media. It is made of a high permeability material, such as a nickel-iron alloy, that helps concentrate the magnetic field at the recording surface. 2. Coil. The coil is a crucial component of the write head as it generates the magnetic field required for writing data. It is typically made of a thin film of copper or aluminum and is wound around a non-magnetic core. When an electric current passes through the coil, it creates a magnetic field that interacts with the recording media. 3. Yoke. The yoke is a magnetic circuit that completes the magnetic flux path in the write head. It is made of a high permeability material, such as a nickel-iron alloy, and helps guide the magnetic field generated by the coil towards the pole tip. 4. Insulation layers. Insulation layers are used to electrically isolate different components of the write head. They prevent current leakage and ensure proper functioning of the write head. 5. Heater. The heater is a unique component in HAMR write heads. It is responsible for locally heating the recording media during the writing process. The heater is typically made of a thin film of a high resistivity material, such as a titanium platinum alloy. When an electric current passes through the heater, it generates heat that raises the temperature of the recording media, making it easier to write data. 7.1.2 Write head operation. The operation of a write head in HAMR involves several steps. 1. Magnetic field generation. When an electric current is passed through the coil, it generates a magnetic field. The magnetic field is concentrated at the pole tip, which is in contact with the recording media. 2. Heating the recording media. Simultaneously, the heater is activated to raise the temperature of the recording media. The localized heating softens the magnetic material on the recording media, making it more receptive to the magnetic field generated by the write head. 3. Writing data. With the recording media heated and the magnetic field generated, the write head applies a magnetic field to the recording media. The magnetic field aligns the magnetic domains in the recording media, effectively writing the desired data. 4. Cooling. After the data is written, the heater is turned off, and the recording media cools down. The cooling process ensures that the written data is stable and retained on the recording media. 7.1.3 Write head design considerations. Designing an efficient write head for HAMR involves several considerations. 1. Magnetic field strength. The write head should generate a strong and focused magnetic field at the pole tip to ensure accurate and reliable data writing. The design of the pole tip and yoke plays a crucial role in achieving the desired magnetic field strength. 2. Thermal stability. The write head should be designed to withstand the high temperatures generated by the heater during the writing process. It should maintain its structural integrity and magnetic properties even under extreme thermal conditions. 3. Size and shape. The size and shape of the write head are important factors in achieving high areal density and data recording density. Smaller write heads allow for tighter track spacing and more data to be recorded in a given area. 4. Material selection. The choice of materials for the various components of the write head is critical. The materials should have high magnetic permeability, good thermal stability, and low electrical resistance. They should also be compatible with the manufacturing processes used to fabricate the write head. 7.1.4 Advancements in write head technology. Over the years, significant advancements have been made in write head technology for HAMR. These advancements have focused on improving the magnetic field strength, thermal stability, and overall performance of the write heads. Some notable advancements include 1. Novel materials. Researchers have explored the use of new materials with improved magnetic and thermal properties for the write head components. These materials offer better performance and reliability, enabling higher data recording densities. 2. Advanced coil designs. New coil designs, such as helical coils and multi-turn coils, have been developed to enhance the magnetic field generation capabilities of the write head. These designs allow for better control and focusing of the magnetic field, resulting in improved data writing accuracy. 3. Integrated heater designs. Efforts have been made to integrate the heater into the write head structure more effectively. This integration reduces the distance between the heater and the recording media, resulting in faster and more efficient heating during the writing process. 4. Nanoscale fabrication techniques. Advancements in nanoscale fabrication techniques have enabled the production of smaller and more precise write heads. These techniques allow for better control over the dimensions and shape of the write head components, leading to improved performance and higher data recording densities. In conclusion, the write head is a critical component in heat-assisted magnetic recording systems. It generates the magnetic field required for writing data onto the recording media and incorporates a heater to locally heat the media. The design of the write head is crucial for achieving accurate and reliable data writing, and advancements in write head technology have led to improved performance and higher data recording densities. 7.2 Write head design for heat-assisted magnetic recording. The write head is a crucial component in heat-assisted magnetic recording (HAMR) technology. It is responsible for generating the localized heat required to facilitate the writing process on the magnetic recording media. The design of the write head plays a significant role in achieving high recording densities and ensuring reliable data storage. In this section, we will explore the various aspects of write head design for HAMR. 7.2.1 Write head components. The write head in HAMR consists of several key components, each serving a specific purpose in the writing process. These components include the main pole, the coil, the waveguide, and the near-field transducer (NFT). The main pole is responsible for generating the magnetic field necessary for writing data onto the recording media. The coil, which is typically made of copper, provides the electrical current required to generate the magnetic field. The waveguide guides the laser light to the NFT, which focuses the light onto the recording media, creating the necessary heat for writing. 7.2.2 Material selection. The choice of materials for the write head is critical to ensure efficient heat generation and reliable operation. The main pole is typically made of a high magnetic moment material, such as a cobalt-based alloy, to achieve a strong magnetic field. The coil is made of a highly conductive material, such as copper, to minimize power losses and maximize the efficiency of the write head. The waveguide and NFT are usually made of materials with high thermal conductivity, such as silicon nitride or aluminum nitride, to efficiently transfer heat from the NFT to the recording media. 7.2.3 Thermal stability. Thermal stability is a crucial consideration in write head design for HAMR. The write head must be able to withstand the high temperatures generated during the writing process without degrading or losing its magnetic properties. To achieve thermal stability, the write head is often designed with a combination of materials that have high melting points and low thermal expansion coefficients. This helps to minimize thermal stress and ensure the longevity of the write head. 7.2.4 Plasmonic near-field transducer. The near-field transducer (NFT) is a key component in the write head that plays a crucial role in HAMR technology. The NFT focuses the laser light onto the recording media, creating the necessary heat for writing. In recent years, plasmonic NFTs have gained significant attention due to their ability to confine light to subwavelength dimensions, enabling higher heat generation and improved writing performance. Plasmonic NFTs utilize surface plasmon polaritons, which are collective oscillations of electrons on the surface of a metal, to achieve highly localized heating. 7.2.5 Design considerations. Several design considerations must be taken into account when designing the write head for HAMR. One important consideration is the size of the write head. As recording densities increase, the write head must be scaled down to accommodate smaller data tracks. This requires careful optimization of the dimensions of the write head components to ensure efficient heat generation and precise writing. Another consideration is the alignment of the write head with the recording media. The write head must be precisely aligned to ensure accurate writing and minimize data errors. Advanced positioning and alignment techniques, such as servo systems and feedback mechanisms, are employed to achieve the required alignment accuracy. Furthermore, the write head design must also take into account the thermal management of the system. Efficient heat dissipation is crucial to prevent overheating and ensure reliable operation. Various thermal management techniques, such as the use of heat sinks or thermally conductive materials, are employed to dissipate heat effectively and maintain the temperature within acceptable limits. 7.2.6 Advancements in Write Head Technology. Over the years, significant advancements have been made in write head technology for HAMR. These advancements have focused on improving the efficiency of heat generation, enhancing thermal stability, and achieving higher recording densities. Researchers have explored novel materials, such as plasmonic materials and magnetic alloys, to improve the performance of the write head. Additionally, advancements in nanofabrication techniques have enabled the fabrication of smaller and more precise write heads, allowing for higher recording densities. 7.2.7 Write head media interactions. The interactions between the write head and the recording media are critical to achieving reliable data storage in HAMR. The write head must be designed to ensure proper contact and minimal spacing between the write head and the recording media. This helps to maximize the efficiency of heat transfer and minimize the risk of data errors. Additionally, the write head design must consider the effects of media properties, such as coercivity and anisotropy, on the writing process to ensure accurate and reliable data storage. In conclusion, the design of the write head is a crucial aspect of heat-assisted magnetic recording technology. The write head components, material selection, thermal stability, and design considerations all play a significant role in achieving high recording densities and reliable data storage. Advancements in write head technology continue to drive the development of HAMR, enabling higher data densities and opening up new possibilities for future applications. 7.3 Advancements in write head technology. The write head is a critical component in heat-assisted magnetic recording (HAMR) technology. It is responsible for generating the localized heat required to facilitate the writing process on the magnetic media. Over the years, significant advancements have been made in write head technology to improve the performance and reliability of HAMR systems. This section will discuss some of the key advancements in write head technology for HAMR. 7.3.1 Plasmonic write heads. One of the major advancements in write head technology for HAMR is the development of plasmonic write heads. Plasmonics is a field that deals with the interaction of light with metallic nanostructures, known as plasmonic nanoparticles. Plasmonic write heads utilize these nanoparticles to enhance the heat generation process in HAMR. By incorporating plasmonic nanoparticles into the write head, the absorption of laser light is significantly increased, resulting in a more efficient heat transfer to the magnetic media. This allows for higher data recording densities and improved writing performance. Plasmonic write heads have shown great promise in overcoming the limitations of conventional write heads and enabling the realization of HAMR technology. 7.3.2 Near-field optical write heads. Another significant advancement in write head technology for HAMR is the development of near-field optical (NFO) write heads. NFO write heads utilize a small aperture or a nanostructured surface to confine the laser light to a subwave-length spot size, enabling highly localized heating of the magnetic media. The use of NFO write heads offers several advantages over conventional write heads. Firstly, the highly localized heating allows for precise control over the writing process, resulting in improved data integrity and reliability. Secondly, the subwave-length spot size enables higher data recording densities, pushing the limits of magnetic storage capacity. Lastly, NFO write heads can operate at lower laser powers, reducing the energy consumption and heat dissipation requirements of HAMR systems. 7.3.3 Advanced materials for write heads. Advancements in materials science have also played a crucial role in improving write head technology for HAMR. The development of new materials with enhanced thermal and magnetic properties has enabled the design and fabrication of more efficient write heads. One such material is the use of high-temperature resistant materials, such as tantalum or titanium nitride, for the write head components. These materials can withstand the high temperatures generated during the writing process without undergoing significant degradation. This ensures the long-term reliability and durability of the write head. Additionally, the use of advanced magnetic materials, such as rare earth magnets or exchange-coupled composite materials, has improved the magnetic field strength and stability of the write head. This allows for more precise and reliable writing on the magnetic media, leading to higher data recording densities and improved overall performance. 7.3.4 Advanced design and fabrication techniques. Advancements in design and fabrication techniques have also contributed to the improvement of write head technology for HAMR. The use of advanced lithography techniques, such as electron beam lithography or nanoimprint lithography, has enabled the fabrication of smaller and more precise write heads. Smaller write heads allow for higher data recording densities, as they can write data in smaller magnetic domains. This leads to increased storage capacity and improved overall performance of HAMR systems. Furthermore, the use of advanced deposition techniques, such as physical vapor deposition or atomic layer deposition, has improved the uniformity and quality of the write head materials, ensuring consistent and reliable performance. 7.3.5 Write head media interactions. Understanding and optimizing the interactions between the write head and the magnetic media is crucial for achieving high-performance HAMR systems. Advancements in write head technology have allowed for better control and manipulation of these interactions. For example, the development of soft underlayers or exchange-coupled composite media has improved the writability and stability of the magnetic media. These advancements ensure that the written data remains stable and reliable over time, even in the presence of external magnetic fields or thermal fluctuations. Furthermore, advancements in write-head design have enabled the optimization of the magnetic field distribution, ensuring that the written data is accurately and consistently recorded on the magnetic media. This has led to improved signal-to-noise ratios and reduced error rates in HAMR systems. In conclusion, significant advancements have been made in write-head technology for heat-assisted magnetic recording (HAMR). The development of plasmonic write-heads, near-field optical write-heads, advanced materials, design and fabrication techniques, and improved write-head media interactions have all contributed to the improvement of HAMR systems. These advancements have enabled higher data recording densities, improved writing performance, and enhanced reliability in HAMR technology. With ongoing research and development, it is expected that write-head technology will continue to evolve, further pushing the boundaries of magnetic storage capacity and enabling new applications in the future. 7.4 Write-head media interactions. In heat-assisted magnetic recording (HAMR), the write-head plays a crucial role in the recording process by generating a localized heat spot on the recording media. This heat spot enables the magnetic grains in the media to be more easily magnetized, allowing for higher areal density and improved data storage capabilities. However, the interactions between the write-head and the recording media are complex and require careful consideration in order to achieve optimal performance and reliability. 7.4.1 Write-head design considerations. The design of the write-head in HAMR systems is critical for achieving precise and controlled heat generation on the recording media. The write-head must be able to deliver a focused and intense heat spot while minimizing any unwanted heat spread to adjacent areas. This requires careful engineering of the write-head's materials, geometry, and thermal properties. One important consideration in write-head design is the choice of materials. The materials used in the write-head must have high thermal conductivity to efficiently transfer heat to the recording media. Additionally, the write-head materials must have high magnetic permeability to ensure efficient magnetic field generation and writing of data. Common materials used in write-head fabrication include magnetic alloys such as permalloy and cofeb. The geometry of the write-head also plays a crucial role in achieving optimal heat generation. The size and shape of the write-head determine the size and shape of the heat spot generated on the recording media. Smaller write-heads can produce smaller heat spots, allowing for higher areal density and increased data storage capacity. However, smaller write-heads also require higher power densities to achieve the necessary heat intensity, which can lead to increased wear and reliability concerns. 7.4.2 Heat transfer mechanisms. The interaction between the write-head and the recording media involves several heat transfer mechanisms. When the write-head generates a heat spot on the media, heat is transferred from the write-head to the media through conduction, convection, and radiation. Conduction is the primary heat transfer mechanism in HAMR systems. It occurs when heat is transferred through direct contact between the write-head and the recording media. The thermal conductivity of the write-head and the media materials determines the efficiency of heat transfer through conduction. Higher thermal conductivity materials allow for more efficient heat transfer, resulting in better heat spot formation and stability. Convection is another heat transfer mechanism that occurs when a fluid, such as air or a lubricant, carries heat away from the write-head and the media. Proper lubrication and cooling of the write-head are essential to prevent overheating and ensure reliable operation. Lubricants with high thermal conductivity and low viscosity are typically used to enhance heat dissipation and reduce friction. Radiation is the transfer of heat through electromagnetic waves. In HAMR systems, radiation plays a minor role in heat transfer compared to conduction and convection. However, it can still contribute to the overall heat dissipation from the write-head to the media. The emissivity of the write-head and the media materials determines the efficiency of heat transfer through radiation. Higher emissivity materials radiate more heat, resulting in improved heat dissipation. 7.4.3 Magnetic field generation and writing. In addition to heat generation, the write-head is responsible for generating a strong and focused magnetic field to write data on the recording media. The magnetic field generated by the write-head must be strong enough to overcome the coercivity of the media and magnetize the magnetic grains in the desired direction. The write-head consists of a magnetic coil that produces a magnetic field when an electric current is passed through it. The geometry and arrangement of the coil determine the shape and intensity of the magnetic field. The magnetic field generated by the write-head is typically perpendicular to the surface of the recording media, allowing for efficient writing of data in the perpendicular recording configuration. The interaction between the magnetic field generated by the write-head and the recording media is influenced by various factors, including the magnetic properties of the media, the distance between the write-head and the media, and the thermal stability of the media. The write-head must be carefully designed to ensure optimal magnetic field generation and writing performance while minimizing any adverse effects on the media, such as thermal decay or erasure of previously written data. 7.4.4 Wear and reliability considerations. The interactions between the write-head and the recording media can have a significant impact on the wear and reliability of HAMR systems. The localized heating and cooling cycles experienced by the write-head and the media during the recording process can lead to thermal expansion and contraction, which can cause mechanical stress and material fatigue. The repeated heating and cooling cycles can also result in thermal decay of the media, where the magnetic properties of the media degrade over time. This can lead to data corruption and loss of storage capacity. Proper thermal management techniques, such as efficient heat dissipation and temperature control, are essential to minimize wear and ensure long-term reliability of HAMR systems. Furthermore, the right-head media interactions can also be influenced by external factors such as humidity, dust, and contaminants. These factors can affect the performance and reliability of the right head in the media, leading to increased error rates and reduced data integrity. Proper environmental control and maintenance are necessary to mitigate the impact of these external factors on HAMR systems. In conclusion, the interactions between the right head and the recording media in HAMR systems are complex and require careful consideration in order to achieve optimal performance and reliability. The design of the right head, including the choice of materials and geometry, plays a crucial role in achieving precise heat generation and magnetic field writing. Additionally, the heat transfer mechanisms, magnetic field generation, and wear and reliability considerations must be carefully managed to ensure long-term operation and data integrity in HAMR systems. 8. Signal processing for heat-assisted magnetic recording. 8.1 Introduction to Signal Processing. Signal processing plays a crucial role in heat-assisted magnetic recording (HAMR) technology. It involves the manipulation and analysis of the recorded signals to ensure accurate and reliable data storage. In this section, we will explore the various aspects of signal processing in HAMR, including error correction coding, signal detection and equalization, as well as the challenges and solutions associated with signal processing in this advanced recording technique. 8.1.1 Error correction coding for heat-assisted magnetic recording. Error correction coding (ECC) is an essential component of HAMR systems, as it helps to mitigate the effects of noise and other distortions that can occur during the recording and readback processes. ECC algorithms are designed to detect and correct errors in the recorded data, ensuring the integrity and reliability of the stored information. In HAMR, the high-density recording and the use of advanced magnetic materials can lead to increased susceptibility to various types of errors, such as thermal fluctuations, media noise, and inter-symbol interference. To address these challenges, sophisticated ECC schemes are employed to provide robust error detection and correction capabilities. One commonly used ECC technique in HAMR is the Reed-Solomon (RS) code. RS codes are powerful error correction codes that can correct a certain number of errors and detect a higher number of errors. These codes are particularly effective in dealing with burst errors, which are common in magnetic recording systems. By adding redundant information to the recorded data, RS codes enable the recovery of lost or corrupted bits, ensuring the accuracy of the retrieved information. Another important ECC technique used in HAMR is the low-density parity check (LDPC) code. LDPC codes are highly efficient in correcting errors and have been widely adopted in modern storage systems. These codes offer excellent error correction capabilities while maintaining a low decoding complexity, making them well suited for HAMR applications. The design and optimization of ECC schemes for HAMR systems require careful consideration of various factors, including the recording density, the characteristics of the magnetic media, and the expected error rates. Researchers and engineers continue to explore new ECC techniques and algorithms to further enhance the error correction capabilities of HAMR systems and improve the overall reliability of data storage. 8.1.2 Signal detection and equalization. Signal detection and equalization are critical aspects of signal processing in HAMR systems. The recorded signals are subject to various distortions during the readback process, such as noise, inter-symbol interference, and thermal fluctuations. Signal detection algorithms are employed to accurately detect and extract the recorded data from these distorted signals. One commonly used technique for signal detection in HAMR is the maximum likelihood sequence estimation (MLSE). MLSE algorithms use statistical models of the recording channel to estimate the most likely sequence of recorded bits given the received signal. By considering the noise and channel characteristics, MLSE algorithms can effectively recover the original data from the distorted signals. Equalization is another important process in HAMR signal processing. It aims to compensate for the inter-symbol interference caused by the finite transition time of the right head and the magnetic media. Equalization algorithms analyze the received signals and apply appropriate adjustments to minimize the effects of inter-symbol interference, ensuring accurate and reliable data recovery. Adaptive equalization techniques are commonly used in HAMR systems to adaptively adjust the equalization parameters based on the characteristics of the recorded signals. These techniques continuously monitor the received signals and update the equalization parameters to optimize the signal recovery process. 8.1.3 Signal processing challenges and solutions. Signal processing in HAMR systems faces several challenges due to the unique characteristics of the technology. The high recording density and the use of advanced magnetic materials introduce new complexities that need to be addressed to ensure reliable data storage. One of the main challenges in HAMR signal processing is the increased susceptibility to thermal fluctuations. The high temperatures involved in the recording process can lead to thermal noise, which can degrade the quality of the recorded signals. Signal processing algorithms need to be robust enough to handle these thermal fluctuations and accurately recover the recorded data. Another challenge is the presence of media noise, which can arise from various sources, such as the magnetic grains in the recording media. Media noise can introduce errors and distortions in the recorded signals, making it more challenging to accurately detect and recover the data. Signal processing techniques need to be designed to effectively mitigate the effects of media noise and ensure reliable data retrieval. Furthermore, the transition from conventional magnetic recording to HAMR technology requires the development of new signal processing algorithms and architectures. The increased recording density and the use of advanced magnetic materials necessitate the exploration of novel techniques to handle the unique challenges posed by HAMR systems. Researchers and engineers are actively working on developing innovative signal processing solutions to address these challenges. Advanced error correction coding schemes, signal detection algorithms, and equalization techniques are being investigated to improve the reliability and performance of HAMR systems. Additionally, machine learning and artificial intelligence techniques are being explored to enhance the signal processing capabilities and optimize the overall data storage process in HAMR technology. In conclusion, signal processing plays a vital role in HAMR technology, enabling accurate and reliable data storage. Error correction coding, signal detection, and equalization are key components of signal processing in HAMR systems. Despite the challenges posed by the high recording density and advanced magnetic materials, ongoing research and development efforts are focused on advancing signal processing techniques to further enhance the performance and reliability of HAMR technology. 8.2 Error correction coding for heat-assisted magnetic recording. Error correction coding plays a crucial role in heat-assisted magnetic recording (HAMR) systems. As the areal density of magnetic recording continues to increase, the susceptibility to errors also rises. Error correction coding techniques are employed to mitigate the impact of these errors and ensure reliable data storage and retrieval. 8.2.1 Introduction to error correction coding. Error correction coding is a technique used to detect and correct errors that occur during data transmission or storage. It involves adding redundant information to the original data, which allows the receiver to identify and correct errors. The choice of error correction coding scheme depends on the desired level of error correction capability, the available resources, and the specific requirements of the HAMR system. 8.2.2 Types of error correction codes. There are various types of error correction codes that can be used in HAMR systems. Some commonly used codes include 8.2.2.1 Reed-Solomon codes. Reed-Solomon (RS) codes are widely used in magnetic recording systems due to their strong error correction capabilities. These codes are based on polynomial arithmetic and can correct a specified number of errors and detect a higher number of errors. RS codes are particularly effective in correcting burst errors, which are common in magnetic recording systems. 8.2.2.2 Low-density parity check codes. Low-density parity check (LDPC) codes have gained popularity in recent years due to their excellent error correction performance. LDPC codes are based on sparse parity check matrices and can achieve near-optimal error correction capabilities. These codes are particularly suitable for high-density storage systems like HAMR, where the number of errors is expected to increase with increasing areal density. 8.2.2.3 Turbo codes. Turbo codes are a class of powerful error correction codes that have been widely used in various communication systems. These codes utilize parallel concatenated convolutional codes and iterative decoding algorithms to achieve excellent error correction performance. Turbo codes are known for their ability to approach the Shannon limit, making them highly suitable for HAMR systems. 8.2.3 Error correction coding techniques for HAMR. In HAMR systems, error correction coding techniques are employed to ensure reliable data storage and retrieval in the presence of thermal fluctuations and other sources of errors. The choice of error correction coding technique depends on factors such as the desired level of error correction capability, the available resources, and the specific requirements of the HAMR system. 8.2.3.1 Concatenated coding. Concatenated coding is a commonly used technique in HAMR systems, where multiple error correction codes are used in a cascaded manner. This approach combines the strengths of different error correction codes to achieve higher error correction capabilities. For example, a combination of Reed-Solomon codes and LDPC codes can be used, where the Reed-Solomon codes correct burst errors, and the LDPC codes handle random errors. 8.2.3.2 Iterative decoding. Iterative decoding is another important technique used in HAMR systems. It involves multiple iterations of the decoding process, where the decoder uses soft information from previous iterations to improve the accuracy of error correction. This iterative process helps to mitigate the impact of errors and improve the overall error correction performance of the system. 8.2.3.3 Adaptive coding. Adaptive coding techniques are employed in HAMR systems to dynamically adjust the error correction coding scheme based on the current operating conditions. These techniques take into account factors such as the signal-to-noise ratio, the temperature of the recording medium, and the error rate to optimize the error correction performance. By adapting the error correction coding scheme, the system can achieve better error correction capabilities under varying conditions. 8.2.4 Challenges and solutions. While error correction coding techniques are effective in mitigating errors in HAMR systems, they also pose certain challenges. Some of the key challenges include 8.2.4.1 Complexity. Error correction coding techniques can be computationally intensive, requiring significant processing power and memory resources. This complexity can pose challenges in terms of implementation and real-time processing. To address this challenge, efficient algorithms and hardware architectures are being developed to optimize the error correction coding process. 8.2.4.2 Latency. The use of error correction coding introduces additional latency in the data storage and retrieval process. This latency can impact the overall system performance, especially in real-time applications. To minimize latency, techniques such as parallel processing and pipelining are employed to optimize the error correction coding process. 8.2.4.3 Trade-off between error correction capability and overhead. Error correction coding introduces overhead in terms of additional data that needs to be stored or transmitted. There is a trade-off between the error correction capability and the overhead introduced by the coding scheme. Finding the right balance between these factors is crucial to ensure efficient and reliable data storage and retrieval in HAMR systems. To overcome these challenges, ongoing research and development efforts are focused on developing advanced error correction coding techniques that offer improved error correction capabilities with reduced complexity and latency. These advancements will play a vital role in enabling the widespread adoption of HAMR technology in various applications. In conclusion, error correction coding is a critical component of heat-assisted magnetic recording systems. It ensures reliable data storage and retrieval by detecting and correcting errors that occur during the recording and readback process. Various error correction coding techniques, such as Reed-Solomon codes, LDPC codes, and turbo codes, are employed to achieve the desired level of error correction capability. However, these techniques also pose challenges in terms of complexity, latency, and the trade-off between error correction capability and overhead. Ongoing research and development efforts are focused on addressing these challenges and advancing error correction coding techniques for HAMR systems. 8.3 Signal detection and equalization. In heat-assisted magnetic recording (HAMR), the process of signal detection and equalization plays a crucial role in achieving high data storage density and reliable data retrieval. As the recording density increases, the signal-to-noise ratio (SNR) decreases, making it challenging to accurately detect and decode the recorded data. Signal detection and equalization techniques are employed to mitigate the effects of noise and distortion, ensuring reliable data recovery. 8.3.1 Signal detection. Signal detection in HAMR involves the extraction of the recorded data from the readback signal obtained from the magnetic recording medium. The readback signal is a weak and noisy representation of the recorded data, making it necessary to employ sophisticated detection algorithms. The primary goal of signal detection is to accurately estimate the recorded data bits from the readback signal. One commonly used technique for signal detection in HAMR is maximum likelihood sequence estimation (MLSE). MLSE takes into account the statistical properties of the recorded data and the noise characteristics to estimate the most likely sequence of recorded bits. MLSE algorithms use a Viterbi decoder to find the optimal sequence of bits that maximizes the likelihood of the observed readback signal. Another popular technique for signal detection is the partial response maximum likelihood (PRML) detection. PRML uses a combination of equalization and detection to estimate the recorded data bits. The equalization process compensates for the intersymbol interference (ISI) caused by the magnetic recording medium, while the detection process estimates the most likely sequence of bits based on the equalized signal. 8.3.2 Equalization. Equalization is a critical step in signal processing for HAMR systems. It compensates for the distortion introduced by the recording medium, such as intersymbol interference (ISI) and nonlinearities. The goal of equalization is to restore the original data waveform, allowing for accurate detection and decoding. One commonly used equalization technique in HAMR is the adaptive equalizer. Adaptive equalization adjusts the equalizer coefficients based on the characteristics of the readback signal. It continuously updates the equalizer to adapt to changes in the recording medium and compensate for the distortion. Adaptive equalization algorithms, such as the least mean squares (LMS) algorithm, estimate the equalizer coefficients by minimizing the mean square error between the equalized signal and the desired signal. Another approach to equalization is the use of decision feedback equalization (DFE). DFE combines feedforward and feedback equalization to mitigate the effects of ISI. The feedforward equalizer compensates for the distortion caused by the recording medium, while the feedback equalizer uses the detected data to further refine the equalization process. DFE algorithms, such as the maximum likelihood sequence estimation (MLSE) algorithm, estimate the equalizer coefficients by considering both the feedforward and feedback paths. 8.3.3 Advanced Signal Processing Techniques. In addition to traditional signal detection and equalization techniques, advanced signal processing methods are being explored to further improve the performance of HAMR systems. These techniques leverage the advancements in machine learning and artificial intelligence to enhance the signal detection and equalization processes. One such technique is deep learning-based signal detection. Deep learning algorithms, such as convolutional neural networks (CNNs) and recurrent neural networks (RNNs), can learn the complex mapping between the readback signal and the recorded data. By training on a large dataset of readback signals and their corresponding recorded data, deep learning models can achieve superior performance in signal detection compared to traditional algorithms. Another area of research is the use of advanced equalization algorithms, such as blind equalization and turbo equalization. Blind equalization algorithms estimate the equalizer coefficients without relying on any training data or prior knowledge of the recording medium. These algorithms use statistical techniques to estimate the equalizer coefficients based on the characteristics of the readback signal. Turbo equalization combines equalization and decoding into a single iterative process, improving the overall performance of the system. 8.3.4 Challenges and Solutions. Signal detection and equalization in HAMR systems face several challenges due to the high recording density and the presence of noise and distortion. Some of the key challenges include nonlinear distortion. The recording medium can introduce nonlinear distortions, which can degrade the performance of signal detection and equalization. Nonlinear equalization techniques, such as Volterra series equalization, are being explored to mitigate the effects of nonlinear distortion. Channel variations. The characteristics of the recording medium can vary across different regions of the disc, leading to variations in the readback signal. Adaptive equalization algorithms that can adapt to these variations are essential to ensure reliable data recovery. Noise and interference. The readback signal is susceptible to various sources of noise and interference, such as thermal noise and inter-track interference. Advanced noise reduction techniques, such as iterative noise cancellation and advanced error correction coding, are employed to mitigate the effects of noise and interference. To address these challenges, researchers are continuously developing innovative signal processing techniques and algorithms. The integration of machine learning and artificial intelligence in signal detection and equalization holds great promise for improving the performance of HAMR systems and enabling higher data storage densities. In conclusion, signal detection and equalization are critical components of HAMR systems, ensuring reliable data recovery in high-density magnetic recording. Traditional techniques, such as MLSE and PRML, are widely used for signal detection, while adaptive equalization and DFE are employed for equalization. Advanced signal processing techniques, including deep learning-based detection and blind equalization, are being explored to further enhance the performance of HAMR systems. Overcoming the challenges posed by nonlinear distortion, channel variations, and noise is crucial for the successful implementation of HAMR technology in future data storage systems. 8.4 Signal processing challenges and solutions. Signal processing plays a crucial role in heat-assisted magnetic recording (HAMR) systems. It involves various techniques and algorithms to ensure accurate and reliable data storage and retrieval. However, the implementation of signal processing in HAMR faces several challenges due to the unique characteristics of the technology. In this section, we will explore these challenges and discuss potential solutions to overcome them. 8.4.1 Signal detection and equalization. One of the primary challenges in HAMR signal processing is the detection and equalization of the recorded signal. The high areal density and the use of heat-assisted writing techniques introduce several complexities that need to be addressed. The recorded signal is affected by various factors such as thermal fluctuations, media noise, and intersymbol interference (ISI). To detect the signal accurately, advanced detection algorithms are required. These algorithms need to account for the noise and distortion introduced during the writing process. Additionally, equalization techniques are employed to compensate for the ISI caused by the high-density recording. Adaptive equalization algorithms, such as maximum likelihood sequence estimation (MLSE), are commonly used to mitigate the effects of ISI and improve the signal quality. 8.4.2 Error correction coding. Error correction coding (ECC) is an essential component of signal processing in HAMR systems. ECC techniques are employed to detect and correct errors that occur during the storage and retrieval of data. However, the increased areal density and the presence of noise and distortion in HAMR pose significant challenges for ECC. The high-density recording in HAMR leads to an increased bit error rate (BER). Traditional ECC schemes, such as Reed-Solomon codes, may not be sufficient to handle the high error rates encountered in HAMR. Therefore, more advanced ECC techniques, such as low-density parity check (LDPC) codes and turbo codes, are being explored to improve the error correction capabilities. Furthermore, the presence of noise and distortion in the recorded signal requires the development of ECC schemes that are robust against these impairments. Iterative decoding algorithms, such as belief propagation, are employed to enhance the error correction performance in the presence of noise and distortion. 8.4.3 Channel modeling and equalization. In HAMR systems, the channel between the write head and the recording media plays a crucial role in signal transmission. The channel characteristics, including the frequency response and the presence of noise, need to be accurately modeled to design effective equalization techniques. Channel modeling in HAMR involves characterizing the frequency response of the channel and identifying the dominant noise sources. The frequency response of the channel is affected by various factors, such as the write head media spacing and the media properties. Accurate modeling of the channel enables the design of equalization filters that compensate for the channel distortions and improve the signal quality. Equalization techniques, such as digital finite impulse response (FIR) filters, are employed to compensate for the channel distortions. Adaptive equalization algorithms, such as least mean squares (LMS) and recursive least squares (RLS), are used to adapt the equalization filters based on the channel characteristics. 8.4.4 Signal processing for servo systems. In addition to data storage and retrieval, HAMR systems require accurate positioning of the read and write heads for servo control. Servo systems in HAMR rely on signal processing techniques to track the position of the heads and maintain precise alignment with the tracks on the recording media. Signal processing for servo systems involves the detection and processing of servo patterns embedded on the recording media. These patterns provide position information that is used to control the movement of the heads. Signal processing algorithms, such as correlation-based detection and phase-locked loops (PLLs), are employed to accurately detect and track the servo patterns. Furthermore, servo systems in HAMR face challenges such as thermal drift and mechanical vibrations, which can affect the positioning accuracy. Advanced signal processing techniques, including adaptive filtering and Kalman filtering, are used to compensate for these disturbances and improve the servo performance. 8.4.5 Real-time processing and hardware implementation. Another challenge in HAMR signal processing is the requirement for real-time processing and hardware implementation. HAMR systems operate at high data rates, and the signal processing algorithms need to be implemented efficiently to meet the real-time processing constraints. Efficient hardware architectures, such as application-specific integrated circuits (ASICs) and field-programmable gate arrays (FPGAs), are used to implement the signal processing algorithms in HAMR systems. These architectures are designed to optimize the computational requirements and memory access patterns of the algorithms, enabling real-time processing. Furthermore, the implementation of signal processing algorithms in HAMR systems requires careful consideration of power consumption and heat dissipation. Power-efficient designs and thermal management techniques are employed to ensure reliable and efficient operation of the signal processing hardware. In conclusion, signal processing in HAMR systems faces several challenges due to the unique characteristics of the technology. The detection and equalization of the recorded signal, error correction coding, channel modeling and equalization, signal processing for servo systems, and real-time processing and hardware implementation are some of the key challenges that need to be addressed. Advanced algorithms, adaptive techniques, and efficient hardware architectures are being developed to overcome these challenges and enable the successful implementation of HAMR technology in high-density data storage applications. 9. Reliability and durability in heat-assisted magnetic recording. 9.1 Reliability challenges in heat-assisted magnetic recording. Heat-assisted magnetic recording (HAMR) is a promising technology that has the potential to significantly increase the storage capacity and data density of magnetic recording systems. However, like any emerging technology, HAMR also faces several reliability challenges that need to be addressed for its successful implementation in practical applications. In this section, we will discuss some of the key reliability challenges associated with HAMR and explore potential solutions to overcome them. 9.1.1 Thermal stability and material degradation. One of the primary reliability challenges in HAMR is ensuring the thermal stability of the recording media and other components under high temperatures. HAMR involves heating the recording media to temperatures above its Curie temperature, which enables the writing of data at higher densities. However, prolonged exposure to high temperatures can lead to material degradation, such as grain growth, diffusion, and phase transformations, which can adversely affect the long-term reliability and performance of the system. To address this challenge, researchers are actively exploring the development of novel recording media materials with improved thermal stability. These materials should have a high Curie temperature and exhibit minimal degradation even under prolonged exposure to high temperatures. Additionally, advanced thermal management techniques, such as localized cooling or heat dissipation, can be employed to minimize the impact of heat on the surrounding components and ensure the overall reliability of the HAMR system. 9.1.2 Laser-induced damage. In HAMR, a laser is used to heat the recording media and facilitate the writing of data. However, the intense laser irradiation can potentially cause damage to the recording media and other nearby components. Laser-induced damage can manifest as thermal stress, material ablation, or even structural changes in the recording media, leading to data loss and reduced reliability. To mitigate laser-induced damage, it is crucial to carefully optimize the laser parameters, such as power, duration, and spot size, to minimize the thermal stress and energy deposition in the recording media. Additionally, the use of protective coatings or materials with enhanced laser resistance can help prevent damage and improve the overall reliability of the HAMR system. 9.1.3 Wear and durability of write heads. The write head is a critical component in HAMR that is responsible for generating the localized heat required for writing data on the recording media. However, the repeated heating and cooling cycles during the operation of HAMR can subject the write head to significant thermal and mechanical stresses, leading to wear and potential failure over time. To ensure the durability and reliability of write heads in HAMR, advanced materials with high thermal stability and mechanical strength are required. Additionally, optimizing the design and manufacturing processes of write heads can help enhance their resistance to wear and improve their overall reliability. Furthermore, implementing effective thermal management techniques, such as heat sinks or active cooling, can help dissipate the heat generated by the write head and minimize its impact on the reliability of the system. 9.1.4 Media head interactions and tribology. In HAMR, the interaction between the recording media and the write head is crucial for achieving reliable and accurate data writing. However, the increased temperature and thermal expansion associated with HAMR can introduce new challenges in terms of media head interactions and tribology. The thermal expansion mismatch between the recording media and the write head can lead to increased friction and wear, affecting the long-term reliability and performance of the system. To address this challenge, researchers are exploring the development of novel lubricants and protective coatings that can reduce friction and wear under high-temperature conditions. Additionally, optimizing the design and surface properties of the recording media and write head can help minimize the contact forces and improve the overall tribological performance of the system. 9.1.5 Environmental and operational factors. Apart from the inherent challenges associated with HAMR technology, the reliability of the system can also be influenced by various environmental and operational factors. Factors such as temperature variations, humidity, shock, and vibration can impact the performance and longevity of the HAMR system. To ensure the reliability of HAMR in real-world applications, it is essential to conduct thorough testing and evaluation under different environmental conditions. This includes subjecting the system to temperature and humidity cycling, mechanical shock, and vibration tests to assess its robustness and reliability. Additionally, implementing effective environmental sealing and protection measures can help minimize the impact of external factors on the performance and reliability of the HAMR system. In conclusion, while heat-assisted magnetic recording (HAMR) holds great promise for increasing the storage capacity and data density of magnetic recording systems, it also presents several reliability challenges. These challenges include thermal stability and material degradation, laser-induced damage, wear and durability of write heads, media head interactions and tribology, as well as environmental and operational factors. Addressing these challenges through the development of advanced materials, optimized designs, and effective thermal management techniques is crucial for the successful implementation of HAMR technology in practical applications. 9.2 Durability considerations. Durability is a critical aspect to consider in heat-assisted magnetic recording (HAMR) technology. As HAMR involves the use of high temperatures and intense laser heating, it is essential to ensure that the recording media, write heads, and other components can withstand the harsh operating conditions over an extended period. In this section, we will explore the various durability considerations in HAMR and discuss the challenges associated with achieving long-term reliability. 9.2.1 Material selection. One of the primary factors influencing the durability of HAMR systems is the selection of materials. The recording media, write heads, and other components must be able to withstand the high temperatures generated during the recording process without undergoing significant degradation. Additionally, these materials should exhibit excellent thermal stability to prevent any unwanted changes in their magnetic properties over time. For the recording media, materials with high Curie temperatures are preferred as they can maintain their magnetic properties at elevated temperatures. Common materials used in HAMR media include iron platinum (FePt) and iron palladium (FePd) alloys, which exhibit high Curie temperatures and excellent thermal stability. Similarly, the write heads must be constructed using materials that can withstand the high temperatures generated during the laser heating process. Materials such as tantalum Ta, titanium T, and various alloys are commonly used in write head fabrication due to their high melting points and thermal stability. 9.2.2 Thermal cycling effects. Thermal cycling, which refers to the repeated heating and cooling of the recording media and write heads, can have a significant impact on their durability. The repeated expansion and contraction of materials during thermal cycling can lead to mechanical stress and potential failure over time. To mitigate the effects of thermal cycling, it is crucial to design HAMR systems with materials that have low coefficients of thermal expansion (CTE). Low CTE materials experience minimal dimensional changes during temperature variations, reducing the mechanical stress on the components. Additionally, the use of advanced thermal management techniques, such as heat sinks and thermal barriers, can help dissipate heat more efficiently and minimize the impact of thermal cycling. 9.2.3 Laser-induced damage. In HAMR, the laser plays a crucial role in heating the recording media to facilitate magnetic recording. However, the intense laser heating can also cause damage to the recording media and write heads if not properly controlled. Laser-induced damage can manifest as thermal degradation, material ablation, or even structural changes in the components. To ensure durability, it is essential to carefully calibrate the laser power and duration to prevent excessive heating and damage. Advanced laser control mechanisms, such as closed-loop feedback systems, can monitor the temperature of the recording media in real time and adjust the laser power accordingly. Additionally, the use of protective coatings on the recording media and write heads can help mitigate laser-induced damage and enhance their durability. 9.2.4 Contamination and wear. Contamination and wear are common challenges in any magnetic recording system, and HAMR is no exception. Contaminants, such as dust particles or lubricants, can accumulate on the recording media or write heads, leading to read and write errors. Similarly, the repeated contact between the write heads and the recording media during the recording process can cause wear and eventual degradation of the components. To address these issues, HAMR systems employ various protective measures. For example, the use of air filters and cleanroom environments can minimize the introduction of contaminants into the system. Additionally, advanced lubrication techniques, such as self-assembled monolayers, can reduce wear and friction between the write heads and the recording media, enhancing their durability. 9.2.5 Environmental factors. Environmental factors, such as temperature and humidity, can also impact the durability of HAMR systems. Extreme temperatures or high humidity levels can accelerate the degradation of materials, leading to reduced reliability and performance. To ensure long-term durability, HAMR systems should be designed to operate within specified temperature and humidity ranges. Additionally, proper storage conditions should be maintained for HAMR media and write heads to prevent any adverse effects on their magnetic properties. 9.2.6 Reliability testing and evaluation. To assess the durability and reliability of HAMR systems, rigorous testing and evaluation procedures are necessary. Various accelerated aging tests can simulate the long-term operating conditions and assess the performance of the components under stress. These tests can include thermal cycling, laser power cycling, and exposure to environmental factors. Reliability testing can help identify potential weaknesses in the system design and materials, allowing for improvements to be made before commercial deployment. Additionally, ongoing monitoring and evaluation of field-deployed HAMR systems can provide valuable insights into their long-term durability and reliability. 9.2.7 Reliability improvement techniques. To enhance the durability and reliability of HAMR systems, several improvement techniques are being explored. These include the development of advanced materials with improved thermal stability, the optimization of laser control mechanisms to minimize laser-induced damage, and the implementation of advanced lubrication techniques to reduce wear. Furthermore, advancements in manufacturing processes and integration techniques can also contribute to improved durability. For example, the use of advanced deposition techniques can ensure uniform and defect-free coatings on the recording media and write heads, reducing the risk of contamination and wear. By addressing these durability considerations and continuously improving the design and materials used in HAMR systems, researchers and engineers can pave the way for the widespread adoption of this promising technology in high-capacity data storage applications. Conclusion. Durability is a critical aspect of heat-assisted magnetic recording (HAMR) technology. The selection of suitable materials, mitigation of thermal cycling effects, prevention of laser-induced damage, and addressing contamination and wear are essential for ensuring the long-term reliability of HAMR systems. By conducting rigorous reliability testing and implementing improvement techniques, researchers and engineers can enhance the durability of HAMR systems and pave the way for their successful integration into high-capacity data storage applications. 9.3 Reliability testing and evaluation. Reliability is a critical aspect of any technology, and heat-assisted magnetic recording (HAMR) is no exception. As HAMR technology continues to advance and move towards commercialization, it is essential to ensure that the systems and components used in HAMR are reliable and durable. Reliability testing and evaluation play a crucial role in identifying potential issues, improving system performance, and ensuring the long-term viability of HAMR technology. 9.3.1 Importance of reliability testing. Reliability testing is the process of subjecting HAMR systems and components to various stress conditions to assess their performance and durability. The goal is to identify any weaknesses or potential failure points and address them before the technology is deployed in real-world applications. Reliability testing is essential for several reasons. Identifying weaknesses. Reliability testing helps identify any weaknesses or vulnerabilities in HAMR systems and components. By subjecting them to rigorous testing, engineers can uncover potential failure modes and design flaws that may not be apparent during normal operation. Improving system performance. Through reliability testing, engineers can gather valuable data on system performance under different conditions. This data can be used to optimize system design, enhance performance, and ensure that HAMR technology meets the required specifications. Ensuring long-term viability. Reliability testing is crucial for ensuring the long-term viability of HAMR technology. By subjecting the systems and components to accelerated aging tests, engineers can simulate the effects of long-term use and assess their durability. This information is vital for predicting the lifespan of HAMR systems and developing strategies to improve their longevity. Meeting industry standards. Reliability testing is often a requirement for compliance with industry standards and regulations. By conducting thorough testing, manufacturers can demonstrate that their HAMR systems and components meet the necessary reliability standards, giving customers confidence in the technology's performance and durability. 9.3.2 Reliability testing methods. Reliability testing involves subjecting HAMR systems and components to a range of stress conditions to evaluate their performance and durability. Several testing methods are commonly used in HAMR reliability testing. Temperature cycling. Temperature cycling involves subjecting the HAMR system to repeated cycles of high and low temperatures. This test helps assess the system's ability to withstand thermal stress and evaluate the reliability of the materials used in its construction. Shock and vibration testing. Shock and vibration testing simulate the mechanical stresses that HAMR systems may experience during transportation or operation. By subjecting the system to controlled shocks and vibrations, engineers can evaluate its resistance to mechanical stress and identify any potential weaknesses. Environmental testing. Environmental testing involves exposing the HAMR system to various environmental conditions, such as humidity, dust, and corrosive gases. This test helps assess the system's ability to withstand harsh environmental conditions and evaluate the reliability of its components. Lifetime testing. Lifetime testing involves subjecting the HAMR system to continuous operation for an extended period. This test helps assess the system's long-term reliability and durability by simulating the effects of prolonged use. Accelerated aging testing. Accelerated aging testing involves subjecting the HAMR system to accelerated aging conditions, such as elevated temperatures and increased stress levels. This test helps predict the system's lifespan and identify potential failure modes that may occur over time. 9.3.3 Evaluation of reliability test results. Once the reliability testing is complete, the test results need to be carefully evaluated to assess the performance and durability of the HAMR system. The evaluation process involves analyzing the data collected during testing and comparing it against the required specifications and industry standards. Some key aspects of evaluating reliability test results include failure analysis. Any failures or issues encountered during the testing process need to be thoroughly analyzed to determine their root causes. This analysis helps identify design flaws, material weaknesses, or manufacturing defects that may have contributed to the failures. Statistical analysis. Reliability test results are often analyzed using statistical methods to assess the system's performance and predict its reliability. Statistical techniques such as Weibull analysis and reliability growth analysis can provide valuable insights into the system's failure rates and reliability characteristics. Comparative analysis. The test results are compared against the required specifications and industry standards to determine whether the HAMR system meets the necessary reliability criteria. Any deviations from the specifications are carefully evaluated to identify areas for improvement. Feedback loop. The evaluation of reliability test results should feed back into the design and development process. Any issues or weaknesses identified during testing should be addressed through design modifications, material improvements, or process changes to enhance the system's reliability. 9.3.4 Reliability improvement techniques. Reliability testing not only helps identify potential issues but also provides valuable insights for improving the reliability of HAMR systems. Based on the test results and evaluation, several techniques can be employed to enhance the reliability of HAMR technology. Design optimization. The design of HAMR systems and components can be optimized based on the insights gained from reliability testing. This may involve improving the structural integrity, enhancing thermal management, or incorporating redundancy to mitigate potential failure modes. Material selection. Reliability testing can help identify materials that exhibit superior performance and durability under stress conditions. By selecting more reliable materials, the overall reliability of HAMR systems can be improved. Process improvements. Reliability testing may reveal process-related issues that affect the performance and durability of HAMR systems. By making process improvements, such as refining manufacturing techniques or implementing stricter quality control measures, the reliability of HAMR technology can be enhanced. Advanced monitoring and diagnostics. Implementing advanced monitoring and diagnostic techniques can help detect potential failures or degradation in real time. By continuously monitoring the system's performance, engineers can take proactive measures to prevent failures and improve reliability. Feedback from field data. Reliability testing should be complemented by feedback from real-world field data. By analyzing the performance and failure data from deployed HAMR systems, engineers can gain valuable insights into the technology's reliability and identify areas for further improvement. Reliability testing and evaluation are essential steps in the development and deployment of HAMR technology. By subjecting HAMR systems and components to rigorous testing, engineers can identify weaknesses, improve system performance, and ensure the long-term reliability and durability of HAMR technology. Through careful evaluation of test results and the implementation of reliability improvement techniques, HAMR technology can continue to advance and meet the demands of future data storage applications. 9.4 Reliability improvement techniques. Reliability is a critical aspect of any technology, and heat-assisted magnetic recording (HAMR) is no exception. As HAMR technology continues to advance, it is essential to address the reliability challenges that may arise. This section will explore various techniques and strategies to improve the reliability of HAMR systems. 9.4.1 Media design and material selection. One of the key factors influencing the reliability of HAMR systems is the design and selection of recording media. The media must be able to withstand the high temperatures generated during the writing process without compromising its magnetic properties. Researchers are actively exploring new materials and designs that can enhance the durability and reliability of HAMR media. One approach is to develop media with improved thermal stability. By selecting materials with higher Curie temperatures, the media can maintain their magnetic properties even at elevated temperatures. Additionally, the use of multi-layered media structures can provide better thermal stability by separating the magnetic layer from the heat source, reducing the risk of thermal degradation. Another consideration is the mechanical durability of the media. The repeated heating and cooling cycles in HAMR can subject the media to thermal stress, which may lead to mechanical failure over time. To address this, researchers are investigating the use of materials with enhanced mechanical properties, such as increased hardness and resistance to wear. By improving the mechanical durability of the media, the reliability of HAMR systems can be significantly enhanced. 9.4.2 Thermal Management Techniques. Efficient thermal management is crucial for ensuring the reliability of HAMR systems. Excessive heat can lead to thermal expansion, which may cause mechanical stress and affect the performance of the system. Therefore, implementing effective thermal management techniques is essential to mitigate these issues. One approach is to optimize the heat sink design. By improving the heat dissipation capabilities of the system, the temperature rise can be minimized, reducing the risk of thermal-induced failures. This can be achieved through the use of advanced heat sink materials with high thermal conductivity, as well as optimizing the heat sink geometry to maximize the surface area for heat transfer. Another technique is the implementation of active cooling methods. By actively removing heat from critical components, such as the right head and media, the temperature can be kept within safe operating limits. This can be achieved through the use of thermoelectric coolers or liquid cooling systems, which can effectively dissipate heat and maintain the system's reliability. 9.4.3 Error Correction Coding. Error correction coding (ECC) plays a vital role in improving the reliability of HAMR systems. ECC algorithms are used to detect and correct errors that may occur during the reading process, ensuring the integrity of the stored data. As the areal density of HAMR systems increases, the susceptibility to errors also increases, making robust ECC techniques essential. Researchers are developing advanced ECC schemes specifically tailored for HAMR systems. These schemes take into account the unique characteristics of HAMR, such as the thermal fluctuations and noise introduced during the writing and reading processes. By optimizing the ECC algorithms, the reliability of HAMR systems can be significantly improved, ensuring accurate and error-free data storage. 9.4.4 Lubricant and Protective Layer Optimization. The lubricant and protective layers in HAMR systems play a crucial role in ensuring the reliability and durability of the media. These layers provide a protective barrier against wear, corrosion, and contamination, which can degrade the performance of the system over time. Researchers are actively exploring new lubricant materials and formulations that can enhance the reliability of HAMR systems. These lubricants must have excellent thermal stability, low volatility, and high resistance to degradation. Additionally, the lubricant must be compatible with the recording media and the right head, ensuring smooth operation and minimizing friction-induced wear. Optimizing the protective layer is also essential for improving reliability. The protective layer should have high hardness and adhesion to prevent mechanical damage and reduce the risk of media contamination. By selecting suitable materials and optimizing the deposition processes, the protective layer can effectively shield the media from external factors, enhancing the reliability and durability of HAMR systems. 9.4.5 Environmental and Operating Conditions. The reliability of HAMR systems can also be influenced by the environmental and operating conditions in which they are deployed. Factors such as temperature, humidity, and vibration can impact the performance and longevity of the system. To improve reliability, it is crucial to design HAMR systems that can operate within a wide range of environmental conditions. This can be achieved through the use of robust and durable materials, as well as implementing effective sealing and encapsulation techniques to protect the sensitive components from external factors. Furthermore, it is essential to consider the operating conditions during the design phase. By optimizing the system's thermal management, power consumption, and operational parameters, the reliability of HAMR systems can be enhanced. This includes ensuring that the system can handle the expected workload and operate within safe temperature limits, minimizing the risk of failures and ensuring long-term reliability. In conclusion, improving the reliability of HAMR systems is crucial for their successful implementation in data storage applications. By addressing the challenges associated with media design, thermal management, error correction coding, lubricant optimization, and environmental conditions, the reliability and durability of HAMR systems can be significantly enhanced. These reliability improvement techniques are essential for ensuring the long-term performance and integrity of HAMR technology in the rapidly evolving data storage industry. 10. Manufacturing and integration of heat-assisted magnetic recording systems. 10.1 Manufacturing processes for heat-assisted magnetic recording systems. Heat-assisted magnetic recording (HAMR) is a cutting-edge technology that has the potential to revolutionize the data storage industry. It offers higher storage densities and improved data reliability compared to conventional magnetic recording techniques. To fully harness the power of HAMR, it is crucial to develop efficient and reliable manufacturing processes for HAMR systems. 10.1.1 Wafer fabrication. The manufacturing process for HAMR systems begins with wafer fabrication. This involves the creation of thin film layers on a substrate, typically made of glass or silicon. The substrate is cleaned and prepared to ensure a smooth and defect-free surface. Various deposition techniques, such as physical vapor deposition (PVD) or chemical vapor deposition (CVD), are used to deposit the different layers required for HAMR systems. The first layer to be deposited is the magnetic recording layer, which consists of a thin film of a magnetic material with high coercivity and high thermal stability. This layer is responsible for storing the data in the form of magnetic bits. The deposition process is carefully controlled to achieve the desired thickness and uniformity of the magnetic recording layer. Next, a protective overcoat layer is deposited on top of the magnetic recording layer. This layer acts as a barrier, protecting the magnetic layer from external factors such as corrosion and wear. The overcoat layer is typically made of a hard material, such as diamond-like carbon (DLC), which provides excellent mechanical and chemical resistance. 10.1.2 Patterning and lithography. After the wafer fabrication process, the next step in manufacturing HAMR systems is patterning and lithography. This involves the creation of precise patterns on the wafer surface to define the locations of the magnetic recording elements, such as the right poles and the reed heads. Photolithography is commonly used for patterning in HAMR manufacturing. It involves the use of a photoresist material that is selectively exposed to ultraviolet (UV) light through a mask. The exposed areas of the photoresist become soluble and are removed, leaving behind the desired pattern. This pattern is then transferred to the underlying layers using etching techniques, such as reactive ion etching (RI) or ion beam etching (IBE). The patterning process is critical for achieving high areal densities in HAMR systems. The dimensions of the magnetic recording elements, such as the track width and the spacing between adjacent tracks, need to be tightly controlled to ensure accurate reading and writing of data. 10.1.3 Integration of heat sources. One of the key challenges in manufacturing HAMR systems is the integration of heat sources. HAMR relies on localized heating of the magnetic recording layer to reduce its coercivity and facilitate writing of data. This requires the integration of a heat source, such as a laser or a near-field optical source, into the HAMR system. The integration process involves precise alignment of the heat source with the magnetic recording elements. This is crucial to ensure that the heat is applied to the correct location on the magnetic recording layer. Various alignment techniques, such as automated optical alignment or mechanical alignment, are used to achieve this. Once the heat source is integrated, it needs to be calibrated and tested to ensure its proper functioning. The power and duration of the heat pulses need to be carefully controlled to avoid overheating or damaging the magnetic recording layer. This calibration process is essential for achieving reliable and consistent performance of the HAMR system. 10.1.4 Assembly and testing. After the integration of heat sources, the HAMR system undergoes assembly and testing. This involves the integration of various components, such as the reed heads, write heads, and control electronics, into a complete HAMR device. The assembly process requires precise alignment and bonding of the different components. This is typically done using advanced bonding techniques, such as flip chip bonding or wire bonding. The alignment and bonding process is critical for ensuring proper functioning of the HAMR system. Once the HAMR device is assembled, it undergoes rigorous testing to ensure its performance and reliability. Various tests, such as read-write tests, thermal stability tests, and environmental tests, are conducted to evaluate the device's functionality under different operating conditions. Any defects or issues identified during testing are addressed and resolved before the HAMR device is considered ready for mass production. 10.1.5 Mass production and quality control. Once the manufacturing processes for HAMR systems are established and optimized, mass production can begin. Mass production involves scaling up the manufacturing processes to produce a large number of HAMR devices efficiently and cost-effectively. Quality control is a crucial aspect of mass production. Strict quality control measures are implemented at various stages of the manufacturing process to ensure that each HAMR device meets the required specifications and performance standards. This includes inspection and testing of the raw materials, in-process inspections, and final product testing. Advanced techniques, such as automated optical inspection (AOI) and statistical process control (SPC), are used to monitor and control the manufacturing processes. These techniques help identify any deviations or abnormalities in the manufacturing process and enable timely corrective actions to be taken. Conclusion. Manufacturing processes for HAMR systems play a vital role in realizing the full potential of this advanced data storage technology. The fabrication of thin film layers, precise patterning, integration of heat sources, assembly, and testing are all critical steps in the manufacturing process. By optimizing these processes and implementing robust quality control measures, manufacturers can ensure the production of reliable and high-performance HAMR systems. 10.2 Integration challenges and solutions. The integration of heat-assisted magnetic recording (HAMR) systems poses several challenges due to the complex nature of the technology. In this section, we will discuss the key integration challenges and explore the solutions that have been developed to overcome them. 10.2.1 Compatibility with existing systems. One of the major challenges in integrating HAMR technology is ensuring compatibility with existing magnetic recording systems. HAMR requires significant changes to the write head, media, and signal processing components, which may not be compatible with the current infrastructure. Upgrading the entire system can be costly and time-consuming. To address this challenge, researchers and manufacturers have focused on developing hybrid systems that can support both conventional magnetic recording and HAMR. This allows for a smooth transition from the existing technology to HAMR without the need for a complete overhaul of the system. By incorporating backward compatibility, the integration process becomes more manageable and cost-effective. 10.2.2 Thermal management. HAMR technology relies on precise and controlled heating of the recording media to reduce its coercivity and enable writing at higher densities. However, this heating process generates a significant amount of heat, which can lead to thermal issues such as overheating and thermal expansion. To ensure proper thermal management, various solutions have been implemented. These include the use of advanced heat sinks and thermal interface materials to dissipate heat efficiently. Additionally, the development of micro-scale cooling techniques, such as microchannels and heat pipes, has been explored to enhance heat transfer and prevent overheating. By effectively managing the thermal aspects of HAMR systems, the reliability and durability of the technology can be improved. 10.2.3 Nanoparticle media interactions. In HAMR, plasmonic nanoparticles are used to enhance the heating process by focusing light onto the recording media. However, the interaction between the nanoparticles and the media can introduce challenges during integration. The nanoparticles may agglomerate or migrate, leading to changes in their optical properties and affecting the overall performance of the system. To address this challenge, researchers have focused on developing stable and well-dispersed nanoparticles that can withstand the harsh operating conditions of HAMR. Surface modifications and coatings have been explored to prevent agglomeration and migration, ensuring the nanoparticles remain in their desired positions. Additionally, advanced fabrication techniques have been developed to precisely control the size, shape, and distribution of the nanoparticles, further improving their stability and performance. 10.2.4 Signal processing and error correction. HAMR technology introduces new challenges in signal processing and error correction due to the increased areal density and the presence of thermal noise. The higher density of data storage requires more advanced signal processing techniques to accurately detect and decode the recorded information. Additionally, the thermal noise generated during the heating process can introduce errors in the recorded data, requiring robust error correction coding schemes. To overcome these challenges, researchers have developed advanced signal processing algorithms and error correction coding schemes specifically tailored for HAMR. These techniques take into account the unique characteristics of HAMR systems, such as the thermal noise and the increased susceptibility to inter-symbol interference. By optimizing the signal processing and error correction algorithms, the reliability and data integrity of HAMR systems can be significantly improved. 10.2.5 Manufacturing processes and equipment. The integration of HAMR technology also requires the development of new manufacturing processes and equipment. The fabrication of HAMR-compatible write heads, media, and other components requires precise and controlled manufacturing techniques. Additionally, the integration of HAMR systems into existing manufacturing lines can be challenging due to the differences in process requirements and equipment. To address these challenges, manufacturers have invested in the development of specialized manufacturing processes and equipment for HAMR. This includes the use of advanced lithography techniques, such as extreme ultraviolet (EUV) lithography, to fabricate high-resolution components. Additionally, the integration of HAMR systems into existing manufacturing lines has been facilitated through the development of modular and adaptable equipment. Conclusion. The integration of HAMR technology into existing magnetic recording systems presents several challenges that need to be addressed. Compatibility with existing systems, thermal management, nanoparticle media interactions, signal processing, and manufacturing processes are among the key areas that require attention. Through innovative solutions and advancements in these areas, the integration of HAMR technology can be achieved, paving the way for higher areal densities and improved data storage capabilities. 10.3 Quality control and testing. Quality control and testing play a crucial role in the manufacturing and integration of heat-assisted magnetic recording (HAMR) systems. As HAMR technology continues to evolve and become more complex, it is essential to ensure that the components and systems meet the required specifications and performance standards. This section will discuss the importance of quality control and testing in HAMR, the various testing methods employed, and the challenges associated with ensuring the reliability and durability of HAMR systems. 10.3.1 Importance of quality control and testing. Quality control and testing are essential in HAMR systems to ensure that the manufactured components and integrated systems meet the desired performance criteria. The reliability and durability of HAMR systems depend on the quality of the individual components and their proper integration. By implementing rigorous quality control measures and comprehensive testing protocols, manufacturers can identify and rectify any issues or defects before the systems are deployed in real-world applications. Quality control and testing also help in optimizing the manufacturing processes and improving the overall efficiency of HAMR systems. By monitoring and analyzing the performance of the components and systems during the testing phase, manufacturers can identify areas for improvement and implement necessary changes to enhance the overall quality and reliability of the HAMR systems. 10.3.2 Testing methods in HAMR. Several testing methods are employed in HAMR to evaluate the performance, reliability, and durability of the components and integrated systems. These testing methods include 10.3.2.1 Component testing. Component testing involves evaluating the individual components used in HAMR systems, such as magnetic recording media, write heads, and heat sources. Various tests are conducted to assess the magnetic properties, thermal stability, and mechanical durability of the recording media. Write heads are tested for their writing and reading capabilities, as well as their compatibility with the recording media. Heat sources are tested for their heating efficiency and uniformity. 10.3.2.2 System testing. System testing involves evaluating the integrated HAMR systems to ensure their proper functioning and performance. This includes testing the write head media interactions, signal processing capabilities, and overall system reliability. System-level tests are conducted to assess the writing and reading performance, error rates, and data integrity of the HAMR systems under different operating conditions. 10.3.2.3 Environmental testing. Environmental testing is performed to evaluate the performance and reliability of HAMR systems under various environmental conditions. This includes subjecting the systems to temperature and humidity variations, mechanical shocks and vibrations, and electromagnetic interference. Environmental testing helps in identifying any potential weaknesses or vulnerabilities in the HAMR systems and enables manufacturers to make necessary design modifications to enhance their robustness. 10.3.3 Challenges in quality control and testing. Quality control and testing in HAMR systems present several challenges due to the complex nature of the technology and the stringent performance requirements. Some of the key challenges include 10.3.3.1 Miniaturization. HAMR systems involve the integration of highly miniaturized components, such as nanoscale recording media and write heads. Testing these miniaturized components requires specialized equipment and techniques that can accurately measure their performance and reliability at such small scales. 10.3.3.2 Thermal considerations. HAMR systems rely on precise thermal control to achieve the desired recording performance. Testing the thermal aspects of HAMR systems, including heat transfer mechanisms and thermal stability, requires sophisticated thermal modeling and simulation techniques. Ensuring accurate thermal testing is crucial to guarantee the reliability and durability of HAMR systems. 10.3.3.3 Data integrity. HAMR systems must maintain high data integrity and low error rates. Testing the signal processing capabilities and error correction coding algorithms is essential to ensure that the HAMR systems can reliably store and retrieve data without any loss or corruption. 10.3.3.4 Long-term reliability. HAMR systems are expected to have long-term reliability and durability. Testing the long-term performance and reliability of HAMR systems is challenging due to the need for extended testing periods and the ability to simulate real-world operating conditions accurately. 10.3.4 Quality control and testing strategies. To overcome the challenges associated with quality control and testing in HAMR systems, manufacturers employ various strategies. These strategies include 10.3.4.1 Advanced testing equipment. Manufacturers invest in advanced testing equipment and techniques that can accurately measure and evaluate the performance and reliability of HAMR components and systems. This includes specialized testing instruments for miniaturized components, high-precision thermal testing equipment, and advanced signal processing and error correction testing tools. 10.3.4.2 Comprehensive testing protocols. Manufacturers develop comprehensive testing protocols that cover all aspects of HAMR systems, including component testing, system testing, and environmental testing. These protocols ensure that all critical performance parameters are thoroughly evaluated and meet the required specifications. 10.3.4.3 Real-world simulation. Manufacturers employ sophisticated simulation techniques to replicate real-world operating conditions during testing. This includes simulating the thermal environment, mechanical stresses, and electromagnetic interference that HAMR systems may encounter in practical applications. Real-world simulation helps in identifying potential issues and improving the reliability and durability of HAMR systems. 10.3.5 Future trends in quality control and testing. As HAMR technology continues to advance, quality control and testing methods are expected to evolve to meet the increasing demands. Some of the future trends in quality control and testing in HAMR systems include development of more advanced testing equipment and techniques to handle the miniaturization and complexity of HAMR components. Integration of artificial intelligence and machine learning algorithms in testing protocols to enhance the efficiency and accuracy of testing processes. Implementation of accelerated testing methods to evaluate the long-term reliability and durability of HAMR systems in a shorter time frame. Collaboration between manufacturers, researchers, and industry organizations to establish standardized testing procedures and performance metrics for HAMR systems. By continuously improving quality control and testing practices, manufacturers can ensure the reliability, durability, and performance of HAMR systems, paving the way for their successful implementation in various applications. 10.4 Manufacturing and integration trends. As heat-assisted magnetic recording (HAMR) technology continues to advance, the manufacturing and integration processes are also evolving to meet the demands of this innovative storage solution. In this section, we will explore the latest trends in HAMR manufacturing and integration, including advancements in manufacturing processes, integration challenges and solutions, and the importance of quality control and testing. 10.4.1 Advanced manufacturing processes. The manufacturing processes for HAMR systems have seen significant advancements in recent years. One of the key areas of improvement is in the fabrication of the recording media. The development of new deposition techniques, such as atomic layer deposition (ALD) and chemical vapor deposition (CVD), has allowed for the precise control of the magnetic properties of the recording media. This level of control is crucial for achieving high areal densities and reliable data storage. Another important aspect of HAMR manufacturing is the fabrication of the write heads. The write heads in HAMR systems require complex structures, including plasmonic waveguides and near-field transducers. Advanced lithography techniques, such as electron beam lithography and nanoimprint lithography, are being used to fabricate these intricate structures with high precision and accuracy. Furthermore, the integration of the heat sources into the HAMR systems has also seen advancements. Laser diodes, which are commonly used as the heat source in HAMR, are being manufactured with improved power output and stability. This allows for more efficient and reliable heat generation, leading to better data writing performance. 10.4.2 Integration Challenges and Solutions. Integrating the various components of a HAMR system presents several challenges. One of the main challenges is the precise alignment of the write head and the recording media. The write head must be positioned accurately over the recording media to ensure optimal heat transfer and data writing. Advanced positioning and alignment techniques, such as optical interferometry and servo control systems, are being employed to achieve this level of precision. Another integration challenge is the thermal management of the HAMR system. The heat generated by the laser diode must be efficiently dissipated to prevent overheating and ensure the reliability of the system. Advanced cooling techniques, such as microchannel heat sinks and thermoelectric coolers, are being used to manage the thermal profile of the HAMR system. Additionally, the integration of the control electronics and signal processing components is crucial for the overall performance of the HAMR system. The control electronics must be designed to handle the high-speed data transfer and processing requirements of HAMR. Advanced integrated circuits and signal processing algorithms are being developed to meet these demands. 10.4.3 Quality Control and Testing. Ensuring the quality and reliability of HAMR systems is of utmost importance. Quality control measures are implemented throughout the manufacturing and integration processes to identify and rectify any potential issues. Advanced inspection techniques, such as scanning electron microscopy and atomic force microscopy, are used to examine the quality of the fabricated components and detect any defects or imperfections. In addition to quality control, rigorous testing is conducted to evaluate the performance and reliability of HAMR systems. Various tests, such as thermal cycling, shock and vibration testing, and data integrity testing, are performed to assess the durability and functionality of the systems under different operating conditions. These tests help identify any weaknesses or areas for improvement in the manufacturing and integration processes. 10.4.4 Manufacturing and Integration Trends. Looking ahead, there are several key trends shaping the future of HAMR manufacturing and integration. One trend is the development of more compact and integrated HAMR systems. Efforts are being made to reduce the size and complexity of the components, while maintaining high performance and reliability. This trend is driven by the increasing demand for smaller and more efficient storage solutions. Another trend is the integration of HAMR technology into existing storage architectures. HAMR systems are being designed to be compatible with current hard disk drive (HDD) form factors and interfaces, allowing for seamless integration into existing data storage infrastructures. This integration enables the adoption of HAMR technology without requiring significant changes to the existing storage ecosystem. Furthermore, advancements in automation and robotics are playing a crucial role in HAMR manufacturing and integration. Automated manufacturing processes and robotic assembly systems are being implemented to improve efficiency, reduce human error, and increase production throughput. These advancements enable faster and more cost-effective production of HAMR systems. In conclusion, the manufacturing and integration of HAMR systems are continuously evolving to meet the demands of this groundbreaking storage technology. Advanced manufacturing processes, integration solutions, and quality control measures are driving the development of more compact, reliable, and efficient HAMR systems. As HAMR technology continues to mature, these trends will shape the future of data storage, enabling higher areal densities and greater storage capacities. 11. Applications and future directions of heat-assisted magnetic recording. 11.1 Current applications of heat-assisted magnetic recording. Heat-assisted magnetic recording, HAMR, is a cutting-edge technology that has the potential to revolutionize the field of magnetic data storage. By utilizing heat to temporarily reduce the coercivity of the recording medium, HAMR enables higher areal densities and increased storage capacities in hard disk drives (HDDs). While HAMR is still in the early stages of commercialization, it holds great promise for a wide range of applications in various industries. 11.1.1 Data centers and cloud storage. One of the primary applications of HAMR technology is in data centers and cloud storage facilities. As the demand for data storage continues to grow exponentially, there is a need for higher capacity and more efficient storage solutions. HAMR offers the potential to significantly increase the areal density of HDDs, allowing data centers to store more data in a smaller physical footprint. This can lead to cost savings in terms of infrastructure and energy consumption, making HAMR an attractive option for large-scale data storage facilities. 11.1.2 High-performance computing. HAMR technology also has significant implications for high-performance computing (HPC) applications. HPC systems require fast and reliable storage solutions to handle massive amounts of data and complex computations. By increasing the storage capacity of HDDs, HAMR can enable HPC systems to store and process larger datasets, leading to improved performance and faster data access. This can have a profound impact on scientific research, simulations, artificial intelligence, and other computationally intensive applications. 11.1.3 Video surveillance and security systems. Video surveillance and security systems generate vast amounts of data that need to be stored and accessed efficiently. HAMR technology can play a crucial role in enhancing the storage capabilities of these systems. With higher areal densities, HAMR-enabled HDDs can store more video footage, enabling longer retention periods and better forensic analysis. Additionally, the increased capacity can support higher resolution cameras and advanced video analytics, improving the overall effectiveness of security systems. 11.1.4 Media and entertainment. The media and entertainment industry is constantly evolving, with the demand for high-quality content growing rapidly. HAMR technology can address the storage requirements of this industry by enabling higher capacity HDDs. This allows for the efficient storage and retrieval of large media files, such as high-definition videos, 3D animations, and virtual reality content. HAMR can also facilitate faster content delivery and streaming, enhancing the user experience for consumers. 11.1.5 Data archiving and long-term storage. Preserving and archiving data for the long term is a critical requirement for many organizations, including government agencies, research institutions, and libraries. HAMR technology can provide a reliable and cost-effective solution for long-term data storage. With its increased storage capacity, HAMR-enabled HDDs can store vast amounts of data for extended periods, ensuring the preservation of valuable information and historical records. 11.1.6 Enterprise storage solutions. Enterprises across various industries rely on robust and scalable storage solutions to manage their data effectively. HAMR technology can offer significant advantages in enterprise storage applications. By increasing the areal density of HDDs, HAMR enables enterprises to store more data in a smaller physical footprint, reducing the overall storage infrastructure costs. This can be particularly beneficial for industries such as finance, healthcare, and e-commerce, where large volumes of data need to be stored and accessed efficiently. 11.1.7 Consumer electronics. HAMR technology has the potential to impact consumer electronics, particularly in devices that require high-capacity storage, such as gaming consoles, smart TVs, and portable media players. With HAMR-enabled HDDs, these devices can offer larger storage capacities, allowing users to store more games, movies, and multimedia content. This can enhance the user experience and provide consumers with greater flexibility in managing their digital content. 11.1.8 Research and development. HAMR technology is still an active area of research and development, with ongoing efforts to further improve its performance and reliability. Research institutions and companies involved in the development of HAMR are exploring new materials, heat sources, and recording media designs to enhance the technology's capabilities. The knowledge gained from these research endeavors can have far-reaching implications beyond data storage, potentially leading to advancements in other fields such as materials science, optics, and nanotechnology. In conclusion, heat-assisted magnetic recording (HAMR) technology has the potential to revolutionize the field of magnetic data storage. Its current applications span across various industries, including data centers, high-performance computing, video surveillance, media and entertainment, data archiving, enterprise storage, consumer electronics, and research and development. As HAMR continues to evolve and mature, it is expected to play a crucial role in meeting the ever-increasing demand for higher capacity and more efficient storage solutions. 11.2 Emerging applications and opportunities. Heat-assisted magnetic recording (HAMR) technology has the potential to revolutionize the field of data storage by enabling higher areal densities and increased storage capacities. While HAMR is primarily being developed for use in hard disk drives (HDDs), there are also emerging applications and opportunities for this technology in other areas. In this section, we will explore some of these emerging applications and discuss the potential opportunities they present. 11.2.1 Data centers and cloud storage. One of the most promising applications of HAMR technology is in data centers and cloud storage. As the demand for data storage continues to grow exponentially, there is a need for higher capacity and more efficient storage solutions. HAMR technology can address this need by enabling higher areal densities, allowing data centers to store more data in a smaller physical footprint. This can lead to significant cost savings and improved energy efficiency in data center operations. Furthermore, the increased storage capacity offered by HAMR technology can also enhance the performance of cloud storage services. With larger storage capacities, cloud service providers can offer more storage options to their customers, allowing them to store and access larger amounts of data in the cloud. This can be particularly beneficial for businesses and organizations that rely on cloud storage for their data-intensive applications. 11.2.2 High-Performance Computing. HAMR technology can also find applications in the field of high-performance computing, HPC. HPC systems require fast and efficient storage solutions to handle the massive amounts of data generated by complex simulations and computations. By enabling higher areal densities, HAMR technology can provide HPC systems with the increased storage capacities they need to handle these large datasets. In addition, the improved energy efficiency of HAMR-based storage systems can also benefit HPC environments. HPC systems consume significant amounts of power, and any reduction in power consumption can lead to cost savings and improved sustainability. By utilizing HAMR technology, HPC systems can achieve higher storage densities while minimizing power consumption, resulting in more efficient and cost-effective storage solutions. 11.2.3 Artificial Intelligence and Machine Learning. Artificial intelligence (AI) and machine learning (ML) applications are becoming increasingly data-intensive, requiring large amounts of storage for training datasets and model parameters. HAMR technology can play a crucial role in supporting these applications by providing higher capacity storage solutions. The increased storage capacity offered by HAMR technology can enable AI and ML systems to store and process larger datasets, leading to more accurate and robust models. This can have a significant impact on various fields, including image and speech recognition, natural language processing, and autonomous systems. With HAMR-based storage systems, AI and ML applications can scale up their storage capabilities to meet the growing demands of these data-intensive tasks. 11.2.4 Archival storage. Another potential application of HAMR technology is in archival storage. Archival storage systems are designed for long-term data retention, typically for several decades or even centuries. These systems require high-density storage solutions that can ensure data integrity and longevity. HAMR technology can provide the necessary storage density for archival storage systems, allowing large amounts of data to be stored in a compact form factor. The thermal stability and reliability of HAMR-based storage media make them well-suited for long-term data retention. By leveraging HAMR technology, archival storage systems can achieve higher storage capacities and improved data preservation, ensuring the long-term accessibility and integrity of archived data. 11.2.5 Consumer electronics. While HAMR technology is primarily being developed for enterprise-level storage solutions, there is also potential for its application in consumer electronics. As consumer devices, such as smartphones, tablets, and laptops, continue to evolve and demand higher storage capacities, HAMR technology can provide a viable solution. By incorporating HAMR-based storage solutions, consumer electronics manufacturers can offer devices with larger storage capacities, allowing users to store more photos, videos, and other data-intensive content. This can enhance the user experience and enable new applications and functionalities on consumer devices. Additionally, the improved energy efficiency of HAMR technology can also contribute to longer battery life in portable devices. Conclusion. As HAMR technology continues to advance, it opens up new applications and opportunities beyond traditional hard disk drives. From data centers and high-performance computing to AI and ML applications, archival storage, and consumer electronics, HAMR technology has the potential to transform various industries by enabling higher storage capacities, improved energy efficiency, and enhanced data integrity. The emerging applications discussed in this section highlight the versatility and potential of HAMR technology, paving the way for a future of more advanced and efficient data storage solutions. 11.3 Future directions and research challenges. Heat-assisted magnetic recording (HAMR) has emerged as a promising technology for achieving higher data storage densities in magnetic recording systems. As the demand for increased storage capacity continues to grow, researchers and industry experts are actively exploring future directions and addressing the research challenges associated with HAMR. In this section, we will discuss some of the potential future directions and the key research challenges that need to be overcome for the widespread adoption of HAMR. 11.3.1 Advanced materials for HAMR. One of the key areas of research in HAMR is the development of advanced materials that can enhance the performance and reliability of the recording media. Current HAMR systems utilize granular perpendicular magnetic recording (PMR) media, but there is a need for materials with higher thermal stability and better writability. Researchers are exploring the use of new materials, such as exchange-coupled composite media and high anisotropy materials, to overcome the limitations of current media. Additionally, the integration of plasmonic nanoparticles into the recording media is being investigated to further enhance the heat-assisted writing process. 11.3.2 Improved heat sources. The development of more efficient and reliable heat sources is another important research direction for HAMR. Current HAMR systems primarily use laser heating, but alternative heat sources, such as near-field optical heating and microwave heating, are being explored. These alternative heat sources have the potential to provide more localized and controlled heating, leading to improved writability and reduced power consumption. However, challenges related to the integration of these heat sources into the recording system and the optimization of their performance need to be addressed. 11.3.3 Thermal Management Techniques. Thermal management is a critical aspect of HAMR systems, as excessive heating can lead to thermal instability and reliability issues. Future research efforts are focused on developing advanced thermal management techniques to ensure the stability and reliability of HAMR systems. This includes the design and optimization of heat sinks, thermal barriers, and other cooling mechanisms to efficiently dissipate the heat generated during the writing process. Additionally, the development of thermal modeling and simulation tools will enable better understanding and control of the thermal behavior in HAMR systems. 11.3.4 Signal Processing and Error Correction. As the areal density of magnetic recording increases in HAMR systems, signal processing and error correction become more challenging. Future research in this area aims to develop advanced signal processing algorithms and error correction codes that can effectively handle the increased noise and interference in high-density HAMR systems. This includes the development of efficient equalization techniques, advanced channel coding schemes, and error detection and correction algorithms. Additionally, the integration of machine learning and artificial intelligence techniques into the signal processing pipeline is being explored to further improve the performance of HAMR systems. 11.3.5 Reliability and Durability. Reliability and durability are critical factors for the successful implementation of HAMR technology in real-world applications. Future research efforts are focused on understanding and mitigating the reliability challenges associated with HAMR systems, such as media degradation, thermal stability, and mechanical wear. This includes the development of advanced testing and evaluation methods to assess the long-term reliability of HAMR systems. Additionally, research is being conducted to identify and implement reliability improvement techniques, such as protective coatings and lubricants, to enhance the durability of HAMR media and components. 11.3.6 Manufacturing and Integration. The manufacturing and integration of HAMR systems present significant challenges due to the complex nature of the technology. Future research in this area aims to develop efficient and cost-effective manufacturing processes for HAMR systems. This includes the optimization of fabrication techniques for recording media, write heads, and other components. Additionally, research is being conducted to address the integration challenges associated with HAMR, such as the alignment of heat sources and write heads, and the development of reliable interconnects and interfaces. 11.3.7 Energy Efficiency. Energy efficiency is a key consideration for any data storage technology. Future research in HAMR focuses on improving the energy efficiency of the technology by reducing the power consumption of heat sources and optimizing the thermal management techniques. This includes the development of low-power heat sources, the integration of energy harvesting techniques, and the optimization of cooling mechanisms to minimize energy losses. Additionally, research is being conducted to explore the use of alternative energy sources, such as solar or waste heat, to power HAMR systems. 11.3.8 Scalability and Compatibility. For HAMR to become a widely adopted technology, it needs to be scalable and compatible with existing infrastructure and standards. Future research efforts are focused on addressing the scalability challenges associated with HAMR, such as the manufacturing of high-density recording media and write heads. Additionally, research is being conducted to ensure the compatibility of HAMR systems with existing magnetic recording technologies, such as PMR and shingled magnetic recording (SMR), to enable a smooth transition to HAMR-based storage solutions. In conclusion, the future of heat-assisted magnetic recording (HAMR) holds great promise for achieving higher data storage densities. However, several research challenges need to be addressed to realize the full potential of HAMR. Advanced materials, improved heat sources, thermal management techniques, signal processing and error correction, reliability and durability, manufacturing and integration, energy efficiency, scalability, and compatibility are some of the key areas that require further research and development. By overcoming these challenges, HAMR has the potential to revolutionize the data storage industry and meet the growing demand for higher capacity storage solutions. 12. Conclusion. 12.1 Summary of key findings. In this book, we have explored the fascinating world of heat-assisted magnetic recording, HAMR, and its potential to revolutionize the field of magnetic recording technology. Throughout the chapters, we have delved into various aspects of HAMR, including its introduction, magnetic materials, heat sources, thermal aspects, nanoparticles and plasmonics, recording media, write heads, signal processing, reliability and durability, manufacturing and integration, and applications and future directions. In this section, we will summarize the key findings from each chapter and discuss the implications and impact of HAMR. 12.1.1 Overview of magnetic recording. In Chapter 1, we provided an introduction to magnetic recording and its evolution over the years. We discussed the need for HAMR, which arises from the increasing demand for higher data storage capacities. HAMR offers the potential to overcome the super-paramagnetic limit and enable higher areal densities in magnetic recording. 12.1.2 Magnetic materials for heat-assisted magnetic recording. Chapter 2 focused on the importance of magnetic materials in HAMR. We explored the different types of magnetic materials and their properties, as well as the advancements in magnetic materials specifically designed for HAMR. The key finding is that the development of new magnetic materials with high thermal stability and magnetic properties is crucial for the success of HAMR. 12.1.3 Heat sources for heat-assisted magnetic recording. In Chapter 3, we discuss the various heat sources used in HAMR, including laser heating, near-field optical heating, and microwave heating. We compared the advantages and limitations of each heat source and highlighted the importance of precise and localized heating for achieving high-density data recording. The key finding is that the choice of heat source depends on factors such as power requirements, heating efficiency, and compatibility with the recording media. 12.1.4 Thermal aspects in heat-assisted magnetic recording. Chapter 4 focused on the thermal aspects of HAMR. We discussed thermal modeling and simulation techniques, heat transfer mechanisms, thermal stability, and reliability considerations. The key finding is that effective thermal management techniques are essential to ensure the stability and reliability of HAMR systems. 12.1.5 Nanoparticles and plasmonics in heat-assisted magnetic recording. In Chapter 5, we explored the role of nanoparticles and plasmonics in HAMR. We discussed the use of plasmonic nanoparticles to enhance the heating efficiency and localized heating in HAMR systems. We also examined the interactions between nanoparticles and the recording media. The key finding is that nanoparticles and plasmonics offer exciting opportunities for improving the performance of HAMR systems. 12.1.6 Recording media for heat-assisted magnetic recording. Chapter 6 focused on the recording media used in HAMR. We discussed the requirements for magnetic recording media, advancements in media technology, and media design considerations. The key finding is that the development of recording media with high coercivity, thermal stability, and writability is crucial for achieving high-density data storage in HAMR. 12.1.7 Write heads for heat-assisted magnetic recording. In Chapter 7, we explored the design and advancements in write heads for HAMR. We discussed the importance of write head design in achieving precise and localized heating. We also examined the interactions between write heads and the recording media. The key finding is that the design of write heads plays a critical role in the performance and reliability of HAMR systems. 12.1.8 Signal processing for heat-assisted magnetic recording. Chapter 8 focused on the signal processing techniques used in HAMR. We discussed error correction coding, signal detection, and equalization methods. We also highlighted the challenges and solutions in signal processing for HAMR. The key finding is that advanced signal processing techniques are necessary to mitigate the effects of noise and interference in HAMR systems. 12.1.9 Reliability and durability in heat-assisted magnetic recording. In Chapter 9, we explored the reliability and durability challenges in HAMR. We discussed the factors that affect the reliability of HAMR systems, durability considerations, reliability testing, and evaluation methods. The key finding is that ensuring the reliability and durability of HAMR systems is crucial for their successful implementation in real-world applications. 12.1.10 Manufacturing and integration of heat-assisted magnetic recording systems. Chapter 10 focused on the manufacturing and integration processes of HAMR systems. We discussed the manufacturing processes, integration challenges, quality control, and testing methods. We also highlighted the trends in manufacturing and integration of HAMR systems. The key finding is that efficient manufacturing and integration processes are essential for the mass production and commercialization of HAMR systems. 12.1.11 Applications and future directions of heat-assisted magnetic recording. In Chapter 11, we explored the current applications of HAMR and discussed the emerging applications and opportunities. We also highlighted the future directions and research challenges in HAMR. The key finding is that HAMR has the potential to revolutionize various industries, including data storage, cloud computing, and artificial intelligence. 12.1.12 Implications and impact of heat-assisted magnetic recording. The implications and impact of HAMR are significant. HAMR has the potential to enable higher areal densities, leading to increased data storage capacities. This can have a profound impact on various industries, including data centers, cloud computing, and big data analytics. HAMR can also contribute to the development of more efficient and powerful computing systems. However, the successful implementation of HAMR requires addressing various challenges, including thermal management, reliability, and manufacturing processes. 12.1.13 Closing remarks. In conclusion, HAMR is a promising technology that can overcome the limitations of conventional magnetic recording and enable higher data storage capacities. The key findings from this book highlight the importance of magnetic materials, heat sources, thermal aspects, nanoparticles and plasmonics, recording media, write heads, signal processing, reliability and durability, manufacturing and integration, and applications and future directions in HAMR. By addressing the challenges and leveraging the advancements in these areas, HAMR can pave the way for the next generation of high-density data storage systems. 12.2 Implications and impact of heat-assisted magnetic recording. Heat-assisted magnetic recording (HAMR) is a revolutionary technology that has the potential to significantly impact the field of magnetic recording. By utilizing heat to enhance the recording process, HAMR offers several implications and benefits that can revolutionize data storage systems. In this section, we will explore the implications and impact of HAMR in various aspects of the industry. 12.2.1 Increased storage density. One of the most significant implications of HAMR is its ability to increase storage density. With traditional magnetic recording technologies reaching their physical limits, HAMR provides a viable solution to overcome these limitations. By using a laser to heat the recording medium, HAMR enables the use of materials with higher coercivity, allowing for smaller magnetic grains and tighter data tracks. This results in a substantial increase in storage capacity, enabling the storage of more data in smaller physical spaces. The increased storage density offered by HAMR has profound implications for various industries and applications. In the data center industry, for example, HAMR can enable higher capacity hard drives, reducing the physical footprint required for storage systems. This can lead to significant cost savings in terms of infrastructure and energy consumption. Additionally, HAMR can have a transformative impact on consumer electronics, enabling smaller and more powerful devices with larger storage capacities. 12.2.2 Enhanced data reliability and durability. Another important implication of HAMR is its potential to enhance data reliability and durability. The use of heat in the recording process allows for more precise and controlled magnetization of the recording medium. This results in improved signal-to-noise ratios and reduced susceptibility to external magnetic fields, leading to higher data integrity. HAMR also addresses the issue of thermal stability, which is a critical concern in magnetic recording. By using localized heating, HAMR can increase the thermal stability of the recording medium, reducing the risk of data loss due to thermal fluctuations. This is particularly important in high-density storage systems where the proximity of magnetic grains can lead to thermal interference. The enhanced data reliability and durability offered by HAMR have significant implications for industries that rely on secure and long-term data storage. In sectors such as finance, healthcare, and government, where data integrity is of utmost importance, HAMR can provide a reliable and robust solution for storing sensitive information. 12.2.3 Energy efficiency and sustainability. HAMR also has implications for energy efficiency and sustainability in the data storage industry. With the increasing demand for data storage and the proliferation of data centers, energy consumption has become a significant concern. HAMR's ability to increase storage density allows for higher capacity drives, reducing the number of drives required to store the same amount of data. This, in turn, leads to lower energy consumption and a smaller carbon footprint. Furthermore, HAMR's improved thermal stability and reliability can contribute to the longevity of storage systems. By reducing the need for frequent data migration and drive replacements, HAMR can help extend the lifespan of storage infrastructure, reducing electronic waste and promoting sustainability. 12.2.4 Technological advancements and innovation. The development and implementation of HAMR technology have significant implications for technological advancements and innovation in the field of magnetic recording. HAMR's unique approach to data storage opens up new possibilities for research and development in areas such as magnetic materials, heat sources, and signal processing. The advancement of magnetic materials for HAMR, such as high coercivity materials and plasmonic nanoparticles, has the potential to drive breakthroughs in material science and engineering. Similarly, the development of more efficient and precise heat sources, such as near-field optical heating, can lead to advancements in laser technology and optics. Furthermore, HAMR's impact on signal processing and error correction coding can drive innovation in data recovery algorithms and techniques. As the complexity of data storage systems increases, the need for advanced signal processing methods becomes crucial. HAMR provides an opportunity to explore new approaches to signal detection, equalization, and error correction, leading to more reliable and efficient data retrieval. 12.2.5 Economic implications and market opportunities. The adoption of HAMR technology can have significant economic implications and create new market opportunities. As the demand for higher capacity storage solutions continues to grow, HAMR can provide a competitive advantage for companies in the data storage industry. By offering increased storage density, enhanced reliability, and energy efficiency, HAMR can attract customers looking for advanced storage solutions. Additionally, the development and commercialization of HAMR technology can stimulate economic growth and job creation. The research, manufacturing, and integration of HAMR systems require expertise in various fields, including materials science, optics, and data storage. This can lead to the establishment of new companies, research collaborations, and job opportunities in these sectors. Furthermore, HAMR's impact on other industries, such as consumer electronics and cloud computing, can create new market opportunities for companies involved in these sectors. The ability to offer smaller and more powerful devices with larger storage capacities can drive innovation and market growth in these areas. In conclusion, heat-assisted magnetic recording (HAMR) has significant implications and impact in various aspects of the data storage industry. From increased storage density and enhanced data reliability to energy efficiency and technological advancements, HAMR offers a promising solution for the future of magnetic recording. The economic implications and market opportunities associated with HAMR further highlight its potential to transform the data storage landscape. As research and development in HAMR continue to progress, it is expected that the full potential of this technology will be realized, leading to a new era of high-capacity and reliable data storage systems. 12.3 Closing Remarks. In this book, we have explored the fascinating world of heat-assisted magnetic recording, HAMR, and its potential to revolutionize the field of magnetic recording technology. We have delved into various aspects of HAMR, including the materials used, heat sources, thermal considerations, nanoparticles and plasmonics, recording media, write heads, signal processing, reliability and durability, manufacturing and integration, and the current and future applications of HAMR. Throughout this journey, we have witnessed the immense progress made in HAMR research and development, as well as the challenges that lie ahead. HAMR offers a promising solution to the ever-increasing demand for higher storage capacities and faster data transfer rates. By utilizing heat to lower the coercivity of the recording media, HAMR enables the recording of smaller magnetic domains, leading to higher areal densities and improved data storage capabilities. One of the key findings of this book is the crucial role played by magnetic materials in HAMR. The advancements in magnetic materials have paved the way for the successful implementation of HAMR technology. The development of new materials with enhanced magnetic properties and performance metrics has significantly contributed to the improvement of HAMR systems. Another important aspect we have explored is the different heat sources used in HAMR. Laser heating, near-field optical heating, and microwave heating have all been investigated as potential heat sources for HAMR. Each heat source has its advantages and challenges, and further research is needed to optimize their performance and efficiency in HAMR systems. Thermal considerations are of utmost importance in HAMR, as the precise control of temperature is crucial for achieving reliable and stable recording. We have discussed thermal modeling and simulation, heat transfer mechanisms, thermal stability, and various thermal management techniques. These aspects are vital for ensuring the longevity and reliability of HAMR systems. The integration of nanoparticles and plasmonics in HAMR has opened up new possibilities for enhancing the performance of HAMR systems. Plasmonic nanoparticles have shown great potential in improving the efficiency of heat delivery to the recording media, thereby enabling higher areal densities and faster data recording. The interactions between nanoparticles and the recording media have also been explored, providing valuable insights into the mechanisms behind HAMR. Recording media and write heads are integral components of HAMR systems. We have discussed the advancements in recording media, including the development of new materials and the design considerations for achieving optimal performance. Similarly, write head technology has evolved to meet the requirements of HAMR, with advancements in design and improved understanding of write head media interactions. Signal processing plays a crucial role in HAMR, as it enables the detection and equalization of the recorded signals. We have explored error correction coding, signal detection, and equalization techniques specific to HAMR. The challenges associated with signal processing in HAMR have been addressed, and potential solutions have been discussed. Reliability and durability are key concerns in any data storage technology, and HAMR is no exception. We have examined the reliability challenges faced by HAMR systems, including thermal stability, media degradation, and write head wear. Various testing and evaluation techniques have been discussed, along with reliability improvement techniques to enhance the longevity and performance of HAMR systems. Manufacturing and integration of HAMR systems present their own set of challenges. We have explored the manufacturing processes involved in HAMR, including the deposition of recording media, fabrication of write heads, and integration of various components. Quality control and testing methods have also been discussed to ensure the production of reliable and high-performance HAMR systems. Finally, we have looked at the current applications of HAMR and the potential future directions of this technology. HAMR has already found applications in high-capacity hard disk drives, but there are emerging opportunities in areas such as data centers, cloud storage, and archival systems. The future of HAMR lies in further research and development to overcome the remaining challenges and unlock its full potential. In conclusion, heat-assisted magnetic recording is a promising technology that has the potential to revolutionize the field of magnetic recording. The advancements in materials, heat sources, thermal considerations, nanoparticles and plasmonics, recording media, write heads, signal processing, reliability and durability, manufacturing and integration, and the current and future applications of HAMR have been explored in this book. While there are challenges to overcome, the future of HAMR looks bright, and it is an exciting time for researchers, engineers, and industry professionals involved in this field.